Hello everyone, welcome to ICCVw23. To clarify, B1 is the binary source workshop, and B2 is the binary north workshop. I repeat, to clarify, B1 is the binary south workshop group, and B2 is the binary north workshop group.
So we'll start shortly. Skip a couple of minutes. And the remote audience, hear me okay? All right, let's get started. Bienvenue à Paris. Welcome to this workshop. Welcome to ICC 2023 workshop on adversarial robustness in the real world. My name is Felix Zhu. I'm currently with Meta AI. So on behalf of the organizers, we warmly welcome you to participate in this workshop, especially those who are here in person, as well as those participating from remotely. So some couple notes before we get started. Our entire day and the session will be recorded for the whole event, and the audience are muted by default. This is regarding the remote audience. And when joining, do not turn on your video. Okay. So regarding asking questions, of course, we'll have Q&A sessions after each speaker. So we have microphones. Our volunteer will be handing out microphones at the back. Thank you. Our remote audience, you'll leave comments in our Zoom chat. So we'll take a couple questions from both the audience, live audience, as well as the remote audience. So this is the Zoom. So just a couple slides in a nutshell. So to motivate why we are here today, right? So we're now here at a computer vision conference for sure. We know deep learning is super successful in computer vision. I'm listing here two very popular data sets everyone knows. ImageNet is the most popular data set for image recognition, for example, the Pascal for object detection. The best result without deep learning, this not the latest, but it's around 75% for ImageNet. The best result without deep learning for Pascal was around 40.9 MAP. And with deep learning, this raised to almost 99% for ImageNet. And best result for Pascal goes to above 90% MAP. But this is the important but here, and this is the reason why we gather here today. The deep learning are also having a lot of problems, right? For example, it can be vulnerable to adversarial noises, adversarial attacks, adversarial perturbations, right? All kinds of adversarial like degradations. Also, it may be poorly generalized to image outside the training data. So this is known as, for example, some OOD problem that we'll hear about today as well. Sometimes it is, the deep learning model is very sensitive to degradations, common corruptions such as occlusions, super low resolution, motion blur, so on and so forth. So all those kind of, factors would affect the deep learning for the computer vision systems. So these are, many of the problems we're trying to solve as a whole, as a community. So today we've gathered 8 experts on these problems to share with us their latest findings. So let me quickly go through the 8 talks of today. So there's a slight change of schedule. So we'll swap number 1, number 2. So we'll begin by listening to Dr. Sharon Lee's talk first, and then we'll go back to Mikel Rodriguez. So Dr. Rodriguez is almost here, so hopefully he'll make it for the second session. Other orderings are unchanged. So we'll begin. Let me quickly go over these topics so you get an idea quickly. So Dr. Sharon Lee will give us a talk on how to safely handle out-of-distribution data in open world, challenges, method, and path forward. So this will be our first talk today. The second talk will be delivered by Mikel Rodriguez on some lessons learned from observed real-world attacks against vision systems. The third talk of today will be from Matthias Hein, adversarial robustness, the good and the ugly. And the fourth talk of today will be given by Dr. Yinpeng on robustness of visual models in the 3D world. So these 4 will be in the morning session, and then we'll have a lunch break with the poster session as well. And when we come back in the afternoon, we'll have the first talk delivered by Dr. Liwei Wang on robust generalization requires exponentially large neural networks. The second talk in the afternoon will be given by Dr. Yisen Wang on rethinking adversarial examples. The third one will be given by Dr. Florian Tramer. Where are the real world attacks? And the final talk of today will be given by Dr. Hazirbas on topics of unveiling model vulnerabilities with the recent robustness dataset. Okay, again, this is morning and afternoon sessions. So I'd like to say, many thanks to our amazing program committees. Without your dedicated reviewing, we won't be here today. Really appreciate your effort reviewing all the paper in such short time frame. So, all right, with that, it's about time. Let's begin our first session, the first talk of the day. So it will be a recorded video of Dr. Sharon Lee. She won't be here with us in person today. Let me fetch that video real quick. All right. Please allow me to introduce our first speaker of today. Dr. Sharon Lee is an assistant professor in the Department of Computer Sciences at the University of Wisconsin-Madison. She's a member of machine learning at UW-Madison and a faculty affiliate with the Data Science Institute. Previously, she was a postdoc researcher in the computer science department at Stanford University with the Hazy group. She completed her PhD from Cornell University in 2017, where she was fortunate to be advised by John E. Hopcroft. Her broad research interest is machine learning. In particular, her research focuses on algorithmic and theoretical foundations for the following research problems, such as out-of-distribution detection, AI alignment, and open-world machine learning. All right, now let me allow me to play the video recorded by Dr. Sharon Lee.
Hi, everyone. Welcome to this presentation on out-of-distribution detection. This is Sharon Lee from the University of Wisconsin-Madison. It's really my great pleasure to be part of this ICCV workshop. And in this presentation, I'll walk you through research challenges and some exciting progress that has been made in this exciting field. Though I couldn't make it to ICCV in person due to some traveling difficulty, I promise you that this talk will be equally exciting. So let's dive in. I want to start the talk by showing you this video. This is a model trained on the Berkeley Deep Drive 100K dataset, performing bounding box tracking on the road. Despite the great performance shown in this demo, the reliability of our machine learning models can often be challenged when we deploy them into the real world. And so in my research, my mission is to encourage both researchers and practitioners to take a more cautious view at these methods and machine learning models that we build, and especially pay attention to those unexpected and potentially unknown situations that the model wasn't trained for. To give you a concrete example, in this slide, we took this image from a data set called MS-COCO, which is completely separate from the training data set. And then we run through this self-driving car model, right, that was just trained on BDD. And concerningly, you can see that model trained on the Berkeley Deep Drive BDD dataset can produce overconfident predictions for this unknown object, helicopter, right in the middle, to be as a truck. And keep in mind that this helicopter was never exposed to the model during the training time, right? So in other words, deep neural networks do not necessarily know what they don't know. And this has raised significant concerns on models' safety and reliability, because you can imagine algorithms that blindly classify such out-of-distribution samples into one of the training categories can be catastrophic. And ideally, in this situation, we want the model to be able to flag such scenario and be able to say something like, I don't know, and maybe I should abstain from making a prediction. So at least human can intervene and take precautions. And this kind of example can manifest in real life, having a real consequence. For example, I'm quoting this news article from last year, which reported that a Tesla vehicle in the self-driving mode crashed into a private jet, which is in blue in this figure here. Fortunately, no one was injured in this event, but you can imagine the gravity of similar incidents in the real world if model doesn't have such safety awareness towards these unknowns. So obviously, this out-of-distribution detection problem has become very, very important, and this is going to be the focus of my talk today. I want to start by providing you with a simple definition, right? So what is out-of-distribution data, you might be asking? To explain to you what this means, let's consider a very simple example where our training data distribution is a mixture of two Gaussians in 2D in this case. So we have class label y equals to 1 and -1 colored in green and blue respectively. And our in-distribution data would be the marginal of this joint data distribution over the input space. So in other words, that's what the green contour is highlighting here, is our in-distribution data Pn. And during deployment, these orange dots could emerge, which are from an unknown class or potentially novel semantics that doesn't belong to y equals to 1 or -1. And therefore, these points should not be predicted by this model that's trained to classify green and blue dots, right? Because these are irrelevant categories for these orange dots. And to translate this toy data into some high-dimensional images, you can think of Cipher 10 on the left-hand side being the in-distribution and SVHN on the right-hand side being OOD. And they have non-overlapping labels with respect to the ID data. And so SVHN is just one of the OOD that the model would encounter. And there are, of course, many other unknowns on this data manifold. So for example, if you look at the right side, you can imagine this to be the natural image manifold that contains all the possible images one could generate and encounter on the internet. And this is a lot more complex compared to the left-hand side, which is our task-specific data set, right? So in other words, the left-hand side is what the model is trained on, and the right-hand side is what the model could potentially run into in the real world. So there's clearly a gap here. So out-of-distribution detection is indeed a non-trivial problem. And I just want to use a few slides to explain the research challenges before we get into the solutions. So the first challenge is the lack of supervision from unknowns during training time. Typically, our models are optimized only on the training data, in this case, the green and blue dots, using empirical risk minimization. And in testing time, you can't really anticipate where these orange dots could emerge in advance, because there can be a huge space of unknowns, especially if you think about higher dimensional space, where the ways that unknowns could emerge are, exponentially more complicated. And this problem is further exacerbated by the high capacity neural networks we're working with nowadays, which have this amazing fitting power, right? To learn to, and with almost, near perfect performance in some cases. However, they could cause problematic decision boundaries when it comes to OOD detection. Or in other words, they can't reliably distinguish ID versus OOD. To explain what I mean, let me use one of my favorite two examples here. So in this figure, let's consider our in-distribution data to be a mixture of three gases. So we have class 1, 2, 3, and we want to train a neural network to perform this, to be able to distinguish among the three classes. And it turns out you can do this fairly easily, even without using, fancier architecture. You don't even need convolutional or transformer networks to do this. If you simply take a multi-layer perceptron, you can do this almost perfectly by achieving 100% classification accuracy. And so this is what the decision boundary looks like if you fit a multi-layer perceptron with a three-way cross-entropy loss. And interestingly, you see here the decision boundary would, have this triangular shape, and any points that's on the bottom left part of this canvas is classified as class 1. And the further you stretch this canvas, the higher confidence is actually it's exhibiting, right? And so red indicates the model is more confident in predicting this to be one of these in-distribution classes. And so obviously this is problematic for the purpose of OOD detection, because those red regions are in fact far away from our training data distribution, right? And therefore they should not be predicted with such high confidence. And one last challenge is that real-world images are composed of numerous objects and components, and therefore we need finer-grained understanding of this OOD uncertainty at the object level, not just the image level. Over the years, we have seen this surge of interest in this challenging problem space. Really, it's great to see this thriving literature on OOD detection. And in this survey paper, my collaborators and I have composed and put together a comprehensive summary for the methods developed in the field. And in this talk, I'll try to unpack some of these techniques. So let's start with a method overview for OOD detection. The model is typically trained on the in-distribution data. say cipher 10 in this case, using empirical risk minimization. So this would simply minimize the average errors or loss that the model is making on the training population. And once the network is trained to converge, we're going to deploy this in the wild, right? And then in testing time, the model would start receiving test time input, which could either be ID or OOD. And so our goal is to devise a scoring function called S here, which takes an input X and compute some scalar based on this neural network F. And if it's above certain threshold, we're going to consider it to be, in distribution and produce the class prediction as usual. And otherwise, if it's below certain threshold, we're going to abstain from making a prediction. So essentially, we're performing a level set estimation, right? Trying to partition all the points in the space into two parts, or two sets, according to this scoring function here. And so this role of OOD scoring function is, in fact, quite central in this picture of OOD detection. And ideally, we want this OOD scoring function to be able to separate ID versus OOD data, just like this illustrative figure here. But in reality, this is not so easily achievable. For example, if we look at a common baseline of using maximum softmax probability, and then here we're plotting for model trained on cipher 10 evaluated against SVHN. This is the resulting distribution for both ID and OOD, which tend to be highly overlapping, right, between the purple and gray distribution. And in fact, this FPR or false positive rate in this case is as high as 50%. So this means when we're choosing this threshold when based upon a large fraction of ID data being correctly classified as ID, at the same time, there is a very high misclassification of OOD data being classified as ID, which is undesirable. So this phenomenon has really triggered a lot of subsequent works on OOD detection, and numerous research efforts have been put into, just designing better OOD scoring functions. And here I'm highlighting a few, including our own works. And today, instead of, focusing on this scoring function part, I want to emphasize the other perspective, which in my view, I think mitigating this OOD risk requires us to think beyond the scoring function design and really rethink how we design the machine learning algorithms from the training time. To explain what I mean, let's revisit this example here, right? Recall this model is trained to classify among class 1, 2, 3 using the common cross entropy loss, right? That tries to minimize the average loss on the in-distribution data. And so the decision boundary, as you see here, is sufficient for this classification performance, almost perfect, but it can be very suboptimal, in fact, problematic for OOD detection purposes. And this is because the existing learning objective, right, is primarily driven to optimize accuracy only on the ID data. But they don't account for uncertainty from outside the in-distribution data. And so going beyond these standard training objectives, we really need to incorporate training time regularization that allows us to explicitly account for OOD uncertainty during training time, right? And so the ideal decision boundary should be something like the right-hand side, which is more aligned with our underlying data density, right? The decision boundary is kind of compactly surrounding these three classes that we have in our training data distribution. And so the question really is, well, how do we go from the left-hand side to the right-hand side without actually performing density estimation, which is a highly intractable problem in high-dimensional space. So to tackle this issue, we put forward these two objectives in learning, which at a high level, you can think of this as a combination of two risks. One, that's the standard classification loss, that's minimizing this cross-entropy loss on the ID data. And additionally, we have this uncertainty regularization, right? That's trying to separate ID versus OOD data. So now let's zoom into the second term, which is more interesting here. So how do we define this, the second term of this loss here? For now, let's assume we have access to some auxiliary outlier training data. This is assumption, I'll come back to Wang later after introducing this objective. But for now, let's assume there is part of the OOD data in training that's available. So given that, our idea is to explicitly push these energy score, which is a measure of OOD uncertainty, right? We want to push this energy score to be as separable as possible between the ID versus OOD data. And so you see in this left figure here, that's really kind of try to separate these two types of data. And just for your reference, here is the definition of how energy is defined, which has this inherent connection to the log likelihood, right? So it's essentially the negative log of the denominator in our softmax function. And if you look at the screen box here, right, this denominator of the softmax actually is proportional to the likelihood of this data point P of X. And so by shaping these energy surface, our objective has some really nice mathematical interpretation. We're essentially performing a level set estimation based on this measurement, right, called energy, which is related to this likelihood of the data points. But this objective is much easier to optimize than performing density estimation directly, because we don't necessarily have to estimate P of X exactly for every single point in the space, right? So it's kind of a easier objective compared to that. All we care about is to have a level set that can distinguish ID versus OOD. And so the result of the training is more separable distribution indeed, like we see in the rightmost figure here, measured by energy. And so this is a model that's trained on Cypher 10 along with an auxiliary outlier data and evaluated against SPHN. And FPR in this case is as low as 1%. And the left two figures are based upon a model trained with standard cross-entropy loss, X score for OOD detection, and the middle one is based on energy score. So you see both are less competitive compared to when we have training time regularization. So this is all promising, but this framework has one caveat. It does require us to have some auxiliary outlier training data, right? And so the question is, where do we even collect those data from? In practice, collecting such large outlier data can be very expensive because we need to perform, manual data collection and cleaning to ensure that the ID and auxiliary outlier training data do not overlap. And moreover, this process needs to be repeated when you switch to a different ID data set, right? So it's not really flexible. And so that triggers us to ask this question: is there any way we can generate OOD data automatically for free, just based on our ID data? And we answered this question in this ICCVw23 paper called the Virtual Outlier Synthesis. And the key idea is to synthesize these outliers in the feature space, which is often having lower dimensionality and therefore more tractable for density estimation purposes. And this suits our purpose because we care more about using them for regularizing models' decision boundary. And here's how this approach works. We're first going to model this feature representation space, in this case as a class conditional multivariate Gaussian distribution. And so here, this purple box highlights the penultimate layer in this neural network, which is layer right before the output layer. And so both the mean and covariance matrix, mu and sigma, can be estimated empirically on the training data set. And once we have those parameters estimated, then we can start sampling from this distribution, right? And then we're going to keep those points, which we call virtual outliers in this dark brown color, from the low likelihood region in this case, right? Meaning they are relatively far away from this distribution. And we can do this for each of the class in our ID data. For example, this figure shows 3 clusters corresponding to 3 classes in the embedding space. And the dark points are the synthesized outliers. And now we can take these synthesized outliers, which have the same dimensionality as our penultimate layer feature, and then we can pass them through the fully connected layer and obtain the model output, right, throughout this shared weights. And so this is essentially a linear transformation from the penultimate layer to the F layer, output layer. And now the energy score can be calculated accordingly based on models' output logits, right? Using this equation here, negative log of summation over the exponential of all this logit. And so now putting everything together, remember that our overall learning goal is to jointly optimize for 2 terms, right? One is the classification accuracy on the ID data, and the second is reliable detection between ID versus OOD. And so the second term is basically pushing the energy score for all the virtual outliers to be above 0, meaning having high OOD uncertainty, and vice versa for our training data distribution to have energy below 0. So that's the overall idea of this framework. I do want to highlight that VOS is a quite general framework that's suitable not only for image classification, but also for object detection. So in case of object detection, the overall learning objective would have 3 terms. So in addition to having classification and uncertainty regularization, we also have the localization. So now, if you recall the example that I showed earlier in this talk, where this helicopter is being misclassified as one of the ID class. Well, it turns out if we're being more careful, conservative in training our neural networks by bringing this uncertainty regularization explicitly, we can do much better to fix this problem. So now this helicopter is successfully detected as an unknown or OOD during the inference time. So admittedly, one limitation in the original VOS framework is the strong distributional assumption that was made on the feature embedding space. And we mitigate this in our follow-up paper called non-parametric outlier census. And I won't go into the details here, but the key idea really is to sample virtual outliers without making any distributional assumption about the feature embedding by employing this non-parametric sampling approach. And so it's suitable for embedding geometry of a variety, right? And therefore it offers kind of stronger generality and flexibility. And just in case you're wondering, if, by adopting these feature space census, we might be losing interpretability because it's hard to kind of see what they look like as opposed to pixel space image census. Well, it turns out you could actually decode these feature space virtual outliers through these powerful diffusion models. And this is our latest work that's going to be presented at NeurIPS this year that showcases some fun examples of how we can generate photorealistic high-resolution outlier images by way of diffusion models. And so this is generating samples with respect to jellyfish, and in this case, it's a ladybug. The in-distribution class is ladybug, but these photos here are the outliers that's being sampled. And so you can actually see what these what the embedding actually correspond to in this pixel space, which is pretty cool. So definitely check out this work if you're interested in learning more about the details. So lastly, beyond the synthesized outliers, you might also be, wondering, can we somehow get these natural outlier training data for free? And the answer is also yes. I think there's very interesting research opportunities around leveraging wild unlabeled data for OOD detection. And so what do I mean by wild data? Let's say you have trained a self-driving car model, right, to classify car, truck, bicycle, and so on. And so once you deploy this model into the real world, you're going to start receiving all kinds of data, right, as the car drives on the road. And all these points are basically coming for free, right? It arrives at these, the server basically on a daily basis. And so the advantage is the data is really available at a great abundance. Every single point is unlabeled without any human annotation. And it's often a much better match to the true test time distribution compared to the data collected offline, because we can actually observe the examples that's coming from these test time OOD. And so mathematically, you can characterize this wild data as a mixture distribution, right? That's a combination of two marginals of P in, which is in distribution, and P out, with some mixing ratio, which is also unknown in practice, called pi here. And so the research challenge here is, the wild data is really heterogeneous, right? And so it's kind of not pure, and it's completely unlabeled. And so the question is, provided with a clean labeled set of ID data together with a large amount of unlabeled wild data that's really noisy, how can we learn to identify a decision boundary between ID versus OOD? And so that's the fundamental question here. And we've made some initial progress. I would highlight these 3 papers, including the one that was just presented at SML earlier this year. So if you're interested, definitely check out these papers for the detailed technical solutions. So lastly, I just want to quickly recap this talk. So in this talk, I've hopefully given you some idea of why OOD detection is an important problem and what are some interesting research challenges out there. In particular, for the methodology, I focus more on this training time regularization, which really aims to learn this more conservative decision boundary that can reliably separate ID versus our OOD data, right? Just like the right side of this figure here. And some of the challenges in designing these learning objective is how do we, collect outlier training data for free? And there are two promising directions. One is to synthesize virtual outliers based upon ID data, and the other one is to leverage this wild unlabeled data that's nonetheless heterogeneous. So I hope this is an informative talk that have helped you better understand this field. And in case you have any further questions, feel free to get in touch with me. And here's my contact information. And I hope you'll enjoy the rest of ICCV. Thank you for watching.
All right, we won't be taking live questions. Please, if you have any questions, please ask Dr. Sharon Lee by emails. All right, let's move on to our next speaker of today. So please allow me to introduce our next speaker. Dr. Mikel works at Google DeepMind, where he's part of an interdisciplinary team that is bringing together new ideas and advances in securing AI-enabled systems. He received his PhD in 2010 while working at UCF's Computer Vision Lab with Professor Mubarak Shah. He then moved to Paris, where he worked as a postdoctoral research fellow at Willow and INRIA ONS project. During his time at INRIA, he worked with Ivan Laptev and Joseph Civic. Dr. Rodriguez, please join me on stage.
Thank you very much. Good to see you here. That's cool. Well, it's great to be here. Good to be back in Paris, and wow, this conference is really evolved from the days when it was just a couple hundred people. Okay. I thought maybe I'd just share a perspective, almost kind of, if you will. This is going to be a little bit more of a kind of a blue collar machine learning security perspective, from like things that we're just kind of seeing in the wild. So you have to excuse me in the sense that the kind of things that we're talking about aren't necessarily super elegant solutions or framing of the problems, but I just wanted to share kind of an in the wild perspective of things. And then hopefully maybe have a back and forth discussion. So first, let me just acknowledge, I mean, it's an incredible time we're living in the sense that, a lot of us have been in this field for a while, and it's just crazy that we've gone from the fact that, now you have in your pocket, you could, pull up and interact with a state-of-the-art machine learning model, and, now it's not a day that goes by that someone in my family isn't, messing around, kind of, basically frontier model. And now we're viewing these systems with incredible access, right? So I think a lot of the people here in this room here care about kind of safe and secure AI in the real world, but we're really kind of elevating the stakes and the challenges in the sense that now we have plugins, we have the ability to have multimodal, we have these kind of new models that are we're still not used to. So I think it's just a very interesting time, and I'll talk a little bit about this at the end. I think the stakes are getting really high, and there isn't much time to work on some of these challenges. So at the same time, I think a lot of us are used to now seeing a lot of the problems that we're working on aren't necessarily just discussed at ICCV, right? They're in the news. I opened up the Washington Post the other day. They're talking about, basically the lack of security in some of these state-of-the-art models. So it's something that is in the public consciousness. We see this as part of public discourse. So in some sense, that also elevates the stakes, right? It's not just an academic exercise anymore. And we went from a very interesting time where we saw this was kind of like an interesting toy academic problem, if you will, without, hopefully disparaging anyone's work. But basically, early on, it was kind of these interesting papers. There was a lot of this kind of Cambrian explosion of research in adversarial machine learning. And all very interesting until we started to see kind of things happen in the real world. In some sense, that's good that we were ahead of the game, but it's also kind of, as we'll see in just a bit, I think taking a turn for a little bit less of what I would have expected. A lot of the kind of early attacks that we saw in papers don't necessarily translate themselves to the real world. You can see. So maybe first, I just wanted to kind of give you a little bit of perspective of where I'm coming from with the problem, just to maybe give a sense. So the kind of things I've been really interested in are kind of high stakes applications of machine learning. So financial data, national security, I've worked in for quite a bit, and I've also worked a lot with like health data. So basically, all of these have something in common in the sense that the stakes are typically pretty high, whether it's privacy or security. You're wanting to think about that lens quite a bit. And in many cases, you have an actual active adversary that is, resourced, has goals, and is actually looking to make your machine learning model fail in some particular way. So that's what I've been up to probably for the past 20-ish years. And I guess the story I want to share with you is I was, a computer vision researcher doing my thing, and then somehow I found myself in the middle of the desert with a whole bunch of like adversarial machine learning patterns in the middle of nowhere. Basically, it's a place called Area 52, which I think a lot of people have heard of with the aliens and everything. But I was doing like an adversarial testing in the real world as part of this kind of government program that was part of the DARPA government program. And I wanted to just share how I got there. I mean, and then what I learned about some of the things that we were seeing in the wild. And let me just maybe share just a little bit more about where I'm coming from. I was mostly focused on just capability development in machine learning. I came a little bit more from the kind of robotics type background. Early on, nothing worked, as you guys know. This was like one of the kind of DARPA grand challenges I participated in. I remember really clearly my little Subaru Outback didn't last more than, I think it was something like 34 seconds on the track before it hit the side of the road. And the reason I bring this up is I think we should also all acknowledge what an incredible time we're living in the sense that this was my life for basically 10 years, right? Just trying to get anything to work. I never imagined being, in the stage talking to people about like security systems because they didn't even work at all. So, I mean, it is kind of jarring to go from spending, a decade trying to get things to work to then now suddenly we're talking about, well, let's make sure these systems are secure against, attackers. So, yeah, it's crazy. We've gone from this, amazing field. I mean, computer vision to me is just such a beautiful problem. And I still, there's a lot of interesting things to deal with, but I think we need to step back for a second, right? We're coming from this long history. And it's incredible that, this little field that started as a summer intern project, now we have to the point of maturity where we're now thinking about some of these kind of higher stakes applications. So how I got to kind of machine learning security focus was, I was working, like I mentioned before, in these different domains, whether it was kind of privacy concern for health, on the national security front, there's, literally kind of nation state adversaries that are kind of going against each other. So kind of it introduced a framing of some of the problems that grounded them and kind of grounded them in some kind of level of reality that really helped them from a research perspective. So that's kind of the background of at least where I'm coming from. And the story I kind of wanted to share a little bit started my kind of the perspective on some of the kind of real world attacks. I was actually just in my office, doing, I think I was, probably reading a archive paper or something like that. And I got a knock on the door by this guy who was like super intense. I mean, I'm just a researcher myself. So I really don't have much history of like dealing with someone from the Pentagon in this case. And they had this problem that was really interesting. Without I guess maybe protecting some of the elements. One of the things, so went into this room and they had all this kind of data that they wanted us to work to help solve. I was working for a national lab, right? So the role of national labs is to help government kind of understand problems. And without getting into like all the super sensitive details, basically what they had was this problem of and I know we're in a computer vision conference, but I'm showing a spectrogram here. And as you guys know, one of the biggest tricks in the audio community is to take their stuff and turn it into an image and use all our good computer vision stuff to solve their problems. So this is an audio problem, but the solution was at the time what was in vogue was basically take an audio and turn it into a spectrogram. And what they were finding was there was this system that is basically, you might have this in your bank, right? I actually am terrified of using it because I know how bad it is. But it's this thing about your voice and your password. So basically they use it as a supplementary biometric. So there was a system, and I won't talk about the specific one now, but basically there was a system that was widely used by a couple of different government agencies that was basically being evaded pretty consistently from like a speaker identification perspective. And the question was like, what's going on? So that's kind of like the framing of the beginning. So, I was going to a lot of these conferences like this one here. So in my head, I had like a huge prior. And my prior was essentially, okay, computer vision person, we've been seeing a lot of these interesting works and things like adversarial input. So I was like, this is like the first time we're seeing some, adversarial input attack in the wild. And, we had a whole, I have my team looking at, clustering this data to see if we could find some of these anomalous patterns and everything. And I really wanted to find that, like, example that this was like a fast gradient sign attack or something like that. But in reality, after digging into a ton of it, it was actually kind of a simple but very clever attack that was actually using an old school like cybersecurity trick, which is basically like a buffer overflow using a malformed JPEG image that was, and there was a weakness in the OpenCV library. So, in some part of me, I was a little bit like disappointed, I'll be honest, in the sense that I was hoping to see an instantiation of some of the cool attacks that we've been seeing and kind of a lot of these conferences. But my first realization is sometimes from an attacker perspective, people are not going to necessarily resort to something that is like academically interesting. It's just going to be something that works for the world. So at the time when we had kind of a similar workshop at CVPR back in 2017, we brought a lot of these people that had this problem into that room, and we said, hey, maybe we need a kind of a larger national red team. And that's when I, takes me to that crazy situation that I was sharing with you early on, where suddenly we went and we said, we need to collect more real world data to see what these attacks would look like. And that's what took me to that crazy in the middle of nowhere desert to collect some adversarial data. And so for about like 6 years, I think the main thing that we were doing is we were basically trying to anticipate what kind of a real world attacker would look like by essentially taking target systems, getting as much intelligence as we can about them by either just like probing them through an API, or reading a paper in terms of like what feasibly this kind of architecture could do. And then you would basically develop a proxy of that model, and then you develop an attack, and then you field that to see how successful it is to kind of test the security of the system. So to give you an idea of what kind of that looked like in real world, I mean, this was just kind of one of the data collections. This was a particular system that used computer vision for some navigation. It's a really terrible quality camera. I still don't understand why. I mean, my cell phone is like vastly superior to the quality of this one, but this is kind of what it looks like on board. And these are like physical adversarial examples in this case that are, fooling the system to kind of hallucinate different objects. So the insight that I had here was this was actually much harder to pull off in terms of like, time of day, is it evening, is it afternoon, the angle of all this stuff. It was significantly more challenging to optimize these patterns to be successful. And we did get it to be successful to get the system to actually hallucinate, as you saw over there. And we did all these fancy things. I remember early on we were doing all these very fancy attacks like infrared for some of these systems. Like there was basically like infrared patterns that were going to be fooling an object detector that's working in infrared. We were even doing things like looking at the emissions of the onboard GPU, basically the FES processing to see if you could infer the architecture just by looking at the emissions of the device itself. So this is like side channel type stuff from the cyber world. And we were really excited. Like this is interesting from both just technically, just interesting that you're able to do this. So one of the insights that I had was that we thought we were being very successful in showing the security of some of these systems, and we had all these plots that looked a lot of like the type of things that we're used to publishing in workshops like here, where you have a attack success rate as a function of some set of parameters. But what I realized was that this is hard to make sense of when you're talking about kind of a fielded kind of real world system, in the sense that when we present these results, and I presented them to this guy over here, and I remember him banging on the table saying, "Hey, well, what does all this mean? If you're telling me that every state-of-the-art system is susceptible to these sort of attacks, like why should we even care, right?" So I think one of the things that I guess I would encourage us to think about is translating those findings that we have of things like attack success rate. We need to be able to kind of show the relevance and the importance from a kind of either a mission or kind of a business perspective. And I do have kind of the open question in my head is, if almost all state-of-the-art systems are susceptible to some of these attacks, what are we really doing, in a sense, if you're looking at it from a security perspective. So I really kind of early on, I really learned that one of the, very humbling experience was, translating from these kind of academic findings to kind of mission level metrics is something that is not obvious, and I'm still learning how to do that, in the sense that I think it's something that was very humbling for me. The other thing that I wanted to share was, I don't know that we have this problem when we're doing, core research, but if you ever find yourself then doing the work that you're doing in kind of in a company or as part of some, organization, I found that it's really important to be, if you're going to be running like a machine learning red team, right, which is the role that I have at Google DeepMind right now. It's really important to be basically empowered to look in the right places and deliver bad news or tricky news. So even though this is not a technical insight, to do this type of work successfully, these red teams really need to be empowered to go and like basically muck around and sometimes deliver some of the hard news. And I'll give you an example of when that didn't happen. There was a company that I was working with that we had this face ID system, and I'm just using an academic data set just to not reveal anything too sensitive. But basically, what we showed was that you were able to back out the training data pretty effectively just by pinging the API. So this is an example of the type of level of detail that we were able to back out, just taking a basically black box prediction API and then pinging it with queries. And this was really concerning in a sense from a privacy perspective. But because at the time, this particular red team was not super empowered, it was just kind of part of some small part of the organization. A lot of these results were just kind of like a little bit ignored. not really fixed, the issues weren't necessarily fixed. So, I guess I would encourage you, if you're going to be taking some of the work that you're doing, make sure that when you're applying this as part of a company, that team, that red team is empowered to do the right thing and to deliver some of that hard news. I guess the other thing that I learned that was a lot of the work that we do, even if you do a really detailed analysis of some of the security, sometimes it gives a false impression that it's like you're giving them like this check of like security. Like I have this team that has looked at different security and privacy issues, and you can get a false sense of security of a machine learning system. So sometimes we need to trade off, being able to do that kind of research and that analysis, but also explain to people that, hey, there's a whole vast world of possibilities here, and this is no guarantee that the system's secure. And that's a challenge that is I've had to kind of continue to hone how to deal with it over the years. So the other thing that I think I alluded to in the beginning was, even though I'm really excited by the very creative attacks that I'm going to be learning out throughout today, many times when I'm looking at real world systems, that what I'm seeing in the wild tends to be, I can't over index on fancy attacks, right? Another thing that I saw as part of the work they were doing, also another kind of fooling of an ID system, but in this case, it was extremely dumb. I mean, it was literally just someone wearing wigs and like using different things. So I bring this up as an example of, if someone is able to achieve an attacker goal with a very low skilled attack, don't discredit that. So I think as a community, looking at machine learning security, it's really important to try to remind yourself and ground yourself in the real world problems. Otherwise, you could be kind of in some kind of exotic land of attacks and defenses that are not grounded in terms of like, wait, would this actually be feasible? Why would someone do this? Do they have a cheaper way of pulling out the same goals? I talked about when I was, out in that, crazy desert doing the adversarial patterns. One of the things that I learned is that it's so easy to go on archive.org and see like every week there's like tens of papers in adversarial machine learning. But translating that from like archive to real world, almost every single time I've tried to do it was much more challenging than you would imagine. So I think that again, from taking the research that you're doing and thinking about real world applications, there's that kind of consideration that you need to have in terms of this is all great on paper and kind of from an academic setting, but is it really something that I should be considered? And many times my experience has been that these attacks aren't very practical in the real world. So the other thing that I wanted to share is that, as a computer vision person, I tend to focus in on the computer vision parts, like the machine learning aspects of the system. But at least like one of the things that has been very humbling for me, as I've been working more, I'll give you an example, like the kind of the Google ecosystem. So many of the products have machine learning, but the machine learning is a tiny little box of this vast system. So I think if the research that this community is doing is going to be impactful, I really encourage us to start thinking about how those machine learning systems interact with the broader system. And actually, that's not to say those things are not interesting. I actually think looking at the broader system introduces a whole new set of research challenges from a kind of adversarial perspective that are very interesting, and I feel like they're underexplored. So I would, this has been really humbling for me. I'll give you an example of something that, there was like a drone system that we were just kind of interested in that had kind of visual odometry and a whole bunch of different navigation elements. But when you looked at the system diagram, it was like this vastly complicated system, right? That had all kinds of elements involving the IMU, and it was doing kind of frame by frame registration. But you can, if you look at that whole system, I mean, you can find these interesting problems. Like the problem that we had was, is there an adversarial attack that will target frame alignment, right? So basically, if you have a video of and it's moving in space, frame to frame alignment is like one of the oldest problems, right? If you look at like the John Pond's book and like in computer vision, from like the original, the OG computer vision book, this is like what they spent chapter 1 and 2 talking about. So this was like multiple key geometry problem. But it turned out that that was the weakness in this particular system. And, you know, we were able to do essentially kind of an adversarial attack that kind of sucked up all those pipe weights, and now the frame alignment, you know, fails. And if you look at the code of the drone system, it kind of has a fail-safe mode that basically lands itself when it's not able to find these pipe weights. So, you know, it's an example that I throw out there that when you look at the broad system, you can find very interesting research problems that lead to real world effect, right? This is not, so I think that kind of looking at the system level is really important. The other thing I wanted to motivate is, you know, as I read papers, many times we talk about black box, white box. I feel like the community needs a better terminology for the vast space that is gray box, because gray box is basically where I live day in, day out, right? And in the real world, you have adversaries are rarely going to be completely in the dark, right? They can read your paper. They say, okay, you know, Google really has this set of architectures, so people usually have an idea. So I think the research community will go, I think, a long way if we maybe start having better frameworks for gradations of gray box that are more realistic, and we could all cite each other's work. So it's not just white, black box, and just some kind of in the middle gray box. So maybe there's opportunities for us to work together here. And examples of gray box knowledge is everything. I mean, as an attacker, if I know your machine learning model is doing classification, that's better than nothing, right? If I know it's doing detection and classification, that's more information. If I know it's deep learning based versus, you know, some like old school SVM, that's information. So I think we need to start thinking about that, kind of how we capture that knowledge. Last thing before I maybe start to, I end with just some kind of open-ended things that we've been thinking about and interested in your thoughts. Is in my day-to-day, most of the use of the type of adversarial attacks that we're used to seeing actually is interesting. I'm seeing it more useful as a kind of defensive mechanism. You know, things like better CAPTCHA systems. So maybe another kind of way for us to start spinning our research here is, I mean, is this set of work maybe less likely to be seen as a person against person? Maybe this is a mechanism for helping kind of some of this kind of machine kind of abuse type stuff that you see with like CAPTCHAs. So that's a pragmatic point, but I think is maybe something that we need to ask ourselves. So, okay, so we're all here together and we care about this topic. So I thought maybe, okay, so I think I talked about this, and hopefully we all agree that the stakes are getting higher. It's no longer kind of a fun and games kind of academic exercise. You know, money and in some cases, you know, lives are on the line. But at the same time, we have this kind of interesting world, right? We have, you know, hardware attacks that are being discovered. We have, it's been proven, my colleague Nicholas Perlini has shown that, you know, it's kind of like poisoning attacks are actually feasible and practical to pull off in the real world. And, you know, we have all this kind of new stuff that's happening, like tool usage that I think is not as explored. So we're kind of at a very interesting time. And maybe I'll end just a little bit with the kind of things that I'm working on, you know, basically in a day-to-day. So as part of DeepMind, we're really trying to like basically put out the next set of, you know, frontier models. And I'll tell you from like a adversarial perspective, it's kind of like the Wild West. I mean, when you think about some of these systems that have the ability to reason and plan and have tool usage and have long memories, I think our work is cut out for us. I mean, it's just really challenging to secure these systems. And I would like to see us move beyond. I'll be honest, I'm like really sick of seeing papers where the first page is like a panda and a given, right? So I think we need to get beyond those type of like panda given attacks, and we need to move into some of these new frontier models. So one of the things that's got me fascinated is this idea of this figure is all messed up. Basically, I think this indirect prompt injection is going to be a massive problem also for computer vision. I started out with LLMs and like language. And for those of you who are familiar, you know, the kind of level one problem is a direct, you have an attacker, and then, well, actually level one problem, the model just is misaligned and has problems. Level two is a person is it has a goal and is directly engaging with the machine learning model. I think most of the papers that we've all been working on up until like last year were all this flavor. And moving forward, at least what I'm seeing is a lot more feasible, practical is basically indirectly attacking the machine learning model. And a lot of these systems right now, so for example, like ChatGPT, right? So ChatGPT is going to have both, multimodal type input, and you could even have it as like an extension on your browser. So now what that means is a third party doesn't necessarily have to directly engage with the machine learning model. They could leave data out in the web. You could be browsing, and then your Chrome extension or whatever it is takes in that input, and now that input is going to then trigger the machine learning model to do something maybe in the various. So I guess if I had to put my little Oracle hat in terms of like, I think very promising area of research is going to be this area of like secure tool usage for machine learning models to include computer vision based VLM type models. So there's all kinds of things, man, I'm sorry, these slides got all messed up, but I think there's going to be kind of this whole taxonomy of tool use attacks of everything from revealing information to doing the wrong thing. This is super early work right now, but I just want to give you a little kind of teaser, for example. You could do it turns out that you could do things with, and you could try this on like some of the open source visual language models, but basically you could go from a pixel attack that basically like pulls up your calendar and then reveals information about when you're free. So those are the sort of things that I think are going to be very valuable from an attacker perspective. It's going to be much more interesting than like turning a panda into a given, because like that doesn't really give you that much value. But as soon as you have people's information, you have actual systems that are behind that have like the value. I think from an attacker perspective, there's going to be a lot of challenges that are going to be coming at us real quick. So this is just an example of something where you can go from image to, in this case, it's a very silly example where we get the model now suddenly with an image to now start talking to us like a pirate. And that's just one like silly example, but you could imagine how, like I mentioned before, you could actually, instead of just getting this model to just talk silly to you, you could actually start getting it to reveal information about some of the things that you plugged into. So, and lastly, before I say that, that's a toy example, at least as part of the Google systems, all of these things are part of vast, like, networks of like, basically a system of systems. So I showed you kind of a little kind of toy academic thing. Proving that in the real world is a whole other challenge. Do I have like 2 more minutes? Yeah, okay. So let me just end real quick. Like basically, I'm very optimistic in general. So I'm actually excited that like I showed all this kind of like, I don't want it to be doom and gloom. So first of all, I think it's really important that we ground our work in like real world data. So one of the things that I've been really passionate about, and I'm hoping to do as part of DeepMind, is have better like publicly available curated data sets that are sanitized, so we're not revealing anything that's like privacy or users or systems, but that are grounded in like this is what was observed in the real world, because I think it'll inspire you and it'll actually kind of ground the research. The other one that I think is really interesting is auto red teaming. So I think it's just gotten exhausting to have attack and defense, attack and defense. It just feels like it's a never-ending thing. So why not just let the machine turn on that? So I think it would be nice to see more work. And basically, at DeepMind we do a lot of stuff with like games, right? So if you imagine like the game of Go, there's all these possibilities. What does that look like for adversarial attacks, right? Can you look at strategies for both attacks and defenses? There's some really interesting work that some of you, I think, have already been working on this front, but I think there's a lot more that can be done. So I think this is a slide from my DEF CON talk, but basically, I think events like this one here give me a lot of optimism in the sense that this community is, growing. So there's a lot of very smart people like you guys working on this. And the last thing I'll say is we're at ICCV, but I think we need to make more friends with the people that are in other communities. Like this is actually a very interesting multidisciplinary field. I think we need to make more friends with some of the folks that are like the cybersecurity team, the folks, and they need to make friends with us. So it would be nice. Maybe one kind of wild idea would be to have a workshop where it is at this intersection of very advanced machine learning models that are not just like, old school SVM, but they're doing these advanced things like, tool usage and memory and planning. But then we bring the problems from both an adversarial machine learning perspective, but then also consider some of the old school tricks from cybersecurity. I think that would be a fascinating, just discussion or event. So with that, I think maybe I'll just pause there and see if there's any questions or comments that I could, elaborate on. Thanks for the time.
If we have any questions, raise your hand. There's Mike down there. Yeah, there's a question there.
Hi, thanks for the talk. Just one question, like, is your team also responsible for looking into the robustness of what said other teams are working into? And if so, are there a set of attacks or methods that you look into before we know that this is good enough for deployment?
Yeah. It's a really two-part thing. So I think another thing that I kind of have been learning, it's been kind of a humbling experience, is that this threshold of like secure enough was like I had to learn the hard way that like it really understanding if this is something that's basically like an OCR system that's just used to like help someone get registered for like a conference versus like something that's being used on like some medical system or maybe the tax record type thing. That like plays heavily in terms of like essentially the risk analysis. And what I didn't know, just as a computer vision person, basically the way it works is there's a two-dimensional axis. So basically you have the feasibility of a particular attack and then like the severity of how bad it would be. So that's kind of the rubric that's used, right? So like, hey, this wouldn't be that bad even if someone could pull it off. So that like likelihood, severity, and likelihood kind of matrix helps make those decisions. In terms of the type of things, I mean, because we're mostly focused on these like kind of, I guess like really kind of advancing state-of-the-art models. The interest for us mostly on some of these new things, basically models that have very long memory, models that have tool usage and extensions to third-party applications, models that have the ability to plan and reason. So those type of things are kind of what interests me right now from a research perspective. Less so than just like here's an image, you would classify it. And I think there's been a lot of work that's been done. Yeah.
Hi, thank you for the great talk again. My question was more about your side talked about having a system level view and what you just said again about the interactions and the software. How would you present it? Like if you were to give a report on, okay, so now I think that the focus is to be done on the interaction, on the access to the model and not the model itself. Like, would you like focus on KPIs? Would you focus on metrics, or would you focus on more like getting a report that talk on, okay, this is the system and having the cybersecurity team, etc. Like, how would you approach?
Yeah, I mean, that's a great question. So I guess maybe one way I would motivate it is you can think of the broader system as you can model it with another machine learning model. So basically right now what we do typically, and what I've noticed is we zoom in, we say this is a convolutional neural net, or this is like a network, and we accept about that little box. But if you zoom out, actually you could model the broader system. We're very comfortable. That's what we do as a machine learning community, right? We model things with so you could in theory say, well, you know what, I'm going to actually take the input and output of the broader system as almost essentially kind of a meta machine learning model. And I'm going to focus on modeling attacks that way. That would be one way. And you could also think about it as a series of cascade of sorts. But I think that leaving that as like work to be done is, I think, a missed opportunity for research, because I think there's actually interesting research problems, and your research will instantly be way more impactful to some of these organizations. Because I think the minute you just start having like just computer vision problem, unless you're fundamentally changing the nature of an adversarial, it's kind of hard to translate that to anything that's practical. Yeah, we're running out.
We're running out of time, so we take that question offline. So let's thank the speaker again. Thank you so much for having us. So our next speaker is Professor Hein. If you're here, please join me on stage. Thank you so much. So we'll help us set up the Zoom and also share screen. Meanwhile, please allow me to introduce our next speaker. So Dr. Matthias Hein is Bosch Endowed Professor of Machine Learning and coordinator of the International Master Program in Machine Learning at the University of Tübingen. His main research interests are to make machine learning systems robust, safe, and explainable, and to provide theoretical foundations for machine learning, in particular deep learning. He serves regularly as area chair for ICML, URPS, and AI Stats, and has been an action editor for Journal of Machine Learning Research from 2013 to 2018. He's an Alice Fellow and has been awarded the German Pattern Recognition Award and an ERC Starting Grant and several Best Paper awards, including URPS, Code, and ARTV. You're the only input.
Now you see it. Okay.
Unmute yourself, share screen. And if you want to open your camera, feel free to.
It seems I cannot do it.
What is this?
It says that the host has deactivated the sharing.
Sorry. And then HDMI. This is HDMI, right?
Yeah.
Yep. Should work. Oh, coming up.
Okay. Good. Yeah, thanks a lot. So, yeah, my talk is a bit more to the core problem. So I'm sorry that this will be more about academic research, not maybe like the talk before, maybe having more the security aspect, but my interest is more like basically how to build robust systems in the first place, right? More from also from a vision perspective, why do these systems are not robust? And basically, I have two aspects here, which I want to address. Maybe the good part is basically I want to show how one can use robust models actually for good things, namely for debugging models and also basically finding out problems of models, which then generalize actually to also non-robust models. And this in the first part, I want to talk basically about the ugly part of adversarial robustness, which I see like this, that even after these kind of years of research in this area, we have not come up with basically models which transfer to other threat models, and we are still struggling basically with scaling up to larger data sets. Okay, and this joint work with my PhD students, Max Augustin, Valentin Borreco, Francesco Koce, Yannick Neuhaus, Christian Schlamann, and Aman Singh. Okay, so yeah, what is the ugly part? I guess we all know this now after, I guess, more than 5 years of research in adversarial robustness. We can't avoid it, right? Basically, all current methods are not adversarial robust. It always hurts also to train robust models. We have this robustness accuracy trade-off. Even so, one can also argue that maybe it's just an additional sample complexity which comes into place. And all what we struggle with is it's difficult to evaluate, right? I don't want to know how many papers which have been published actually have published wrong results, in the sense that their models are actually much less robust than claimed. And I think there's also a problem if you think about the AI Act asks actually for robustness, but if even we as a community are not able to evaluate this correctly, right? How should then, let's say, an agency, a government agency, evaluate this? And we have come up with AutoAttack some years ago, and this is, I think, now a standard relation for the P defense for image classification. And I guess the good thing about AutoAttack is it has no free parameters, right? You cannot basically do something wrong because you just apply it. But one also has to admit that AutoAttack really is no universal tool, right? I mean, basically, it is only aiming at a certain class of defenses, but it cannot deal with all kinds of defenses, which is really a problem, like test time defenses and so on. Then even certified methods can fail. So last year we had, or this year actually, we had a paper where we showed that randomized smoothing can actually give you false certificates if you use floating point arithmetic. And then we proposed a fix to this. So even so, I have to admit that this false certificates are most likely not a problem for the standard classifiers. And now the main part, I think, which is interesting for this talk, is this, basically we have no transfer of robustness. So we can train for one thread model, but basically then, if we just try out a different thread model, like we train for L-infinity thread model and test for L1, then basically we are typically not robust. And that's clearly a game which is annoying, because it seems we are not really making progress towards real robust models. And then the last question is basically, clearly training adversarial robust models is still super expensive, and therefore even robust ImageNet models are still rare. And now clearly, as we have seen also in the last talk, the question is basically how we get actually robust foundation models. Okay, so in the first part, I want to talk a bit about recent work on robust ImageNet models and what is actually the influence of the architecture. I mean, when basically vision transformers came out 2 or 3 years ago, there was immediately some papers claiming that VITs maybe have better properties in terms of robustness. And that's basically what we want to have a look at in terms of adversarial robustness here. Okay, and here you see a landscape basically of the current ImageNet robust models. So on the x-axis, you have the number of parameters. On the y-axis, you have the robust accuracy. You see basically all the kind of state-of-the-art models. And basically these red models are our ConfNext models with this additional conf-stem. And I will come back to this in a second. And here are our VIT models, and which also have this conf-stem extension. Now from this plot, it looks like, okay, VIT is maybe a bit worse than ConfNext. Yeah, so it's not better in terms of robustness. But there is an interesting fact to this, which, I come to in a second. Okay, but before that, one major thing, and that actually turned out to be more important than ConfNext versus VIT, was actually this little change of the architecture. And the little change of the architecture was what we did was we actually replaced the patch stem with a conf stem. The patch stem basically you all know it from transformers. Basically, you have a patch-based approach, right? You have 16 by 16 or 32 by 32 patches initially for downsampling, and even the ConfNext uses 4x4 patches. And now the simple thing was basically you replace this downsampling by just a convolution. Yeah. And just this simple change of the architecture leads then to the fact that you have never degradation in L-infinity robust accuracy. You most of the time actually improve, but the important thing is actually that you improve generalization to unseen L1 and L2 thread. Yeah, so you have actually a better generalization to other thread models which you have not seen before. Now, another important thing for training actually these robust models was basically a very important part is that you need a clean model as initialization. If you start training from scratch, basically, typically this fails. In particular, it fails then to use heavy augmentation. And heavy augmentations used then during training are actually the key to really get to high robustness, but also high clean accuracy of these models in the end. What is less maybe important is the number of attack steps which you use. So we use always 2 adversarial steps for training these ImageNet models, but you can also get this more or less the same result with 1 step, and you don't improve that much if you use 3 steps indeed. Also, we trained here these models for 300 epochs, but you can basically get also for 50 epochs already reasonable results for a ConfNext architecture. For VIT, basically one has to say here, the additional training time is really necessary. Otherwise, you have really a drop of up to 4% in robust accuracy, which is clearly, a lot. Now, the interesting part is, as I said, this change from patch stem to conf stem. Yeah, and you basically can just look at the last 2 lines. Here is basically the ConfNext with the conf stem architecture. It has the best results, and the ConfNext, the original ConfNext, has slightly less worse results here, right, in clean accuracy and also an infinity robust accuracy. I should say we train for radius of 4 over 255. But then the striking thing is if you actually evaluate the unseen threat models, right? We have not trained for L2 and L1, and but we just evaluate the robustness. And what you see is basically you have a drop of, or you can see it like this, the conf stem, replacing patch stem by conf stem leads to improvement in these threat models by up to 10%. And this is also the same for the VIT. For the VIT, basically, you have actually a larger improvement even in robust accuracy in L infinity, but you have even a much larger improvement in L2 and L1 in these unseen threat models. So you see basically that this small difference, patch stem to conf stem, has a much larger influence than basically ConfNext versus VIT. And this was for small architectures. This also generalizes to larger architectures. And again, here, the ConfNext basically has the best infinity robust accuracy, but the transformer has the, much better generalization for unseen threat models. Yeah, so now it depends basically what you want, right? Do you want to have best infinity robust accuracy? Then it's ConfNext. But if you want to have a model which has basically good generalization properties to other threat models, then the VIT is basically the model to choose. What is also interesting for the ImageNet models is basically that you can vary the input resolution at test time, right? So typically we train here at 224 resolution, but it has been shown also for clean models before that just increasing the test time resolution can improve the clean accuracy. Now, what is actually surprising is that also the L infinity robust accuracy goes up if you increase the test time resolution. And why is that surprising? Because basically the threat model becomes more powerful, right? If you have more pixels to attack, if you increase the input resolution, your threat model becomes more powerful. So actually you expect that the robust accuracy goes down, but instead it actually goes up, and you can get quite significant improvements by just upscaling the image resolution. And again, here the conf stem model seem to profit from this increasing test time resolution much more than the patch stem model. Yeah, you see here severe degradation actually of these patch stem models. Yeah, and then coming basically seeing, we know that ImageNet models can be quickly fine-tuned for a lot of data sets, and now the goal would be also that these robust ImageNet models basically become the same blueprint models for other data sets. And we also show this, that basically then just fine-tuning these robust models for a very small number of epochs to these small data sets yields actually to results which are not state-of-the-art. Yeah, these results are, they're in particular with additional synthetic data now for Cypher 100, Cypher 10, much better results have been shown. But these results are pretty reasonable, and in particular they have actually for their robustness quite a high clean accuracy. Okay, so this is shows basically how robust ImageNet models can basically used for a lot of tools. And now I want to show basically that robust ImageNet models can also useful for robust semantic segmentation. Yeah, so semantic segmentation, basically now the task is not to just predict the decision for each image, but basically predict the class for each pixel of the image. Yeah, so we get basically this kind of result. And yeah, it's not surprising that the normally trained model you can easily attack, right? So here we do a target attack with grass or sky, and you can basically destroy the full segmentation easily. But basically our robust model is then basically you see almost no change when you attack it. This semantic segmentation is actually an interesting problem, because now you have to change all the decisions of all the pixels, not just the decision of a single image. And that is a much more challenging attack problem than the usual image classification. And we basically developed a new attack of ensemble and showed then again an overestimation of existing attacks, but I don't want to talk about this. I want to talk rather that there are not many L-infinity robust models in this area. And basically there are only available two, and one of them turns out to be absolutely non-robust. So the authors have used some variant of adversarial training, but basically the models are absolutely non-robust. And the other models, basically in this FactPGD paper, they claim robustness, and I think they are also robust, but unfortunately they are not available, so we could not test them. But the main point I want to make is basically again that once you have robust ImageNet models, then also you can basically, for so to say downstream tasks or related tasks, you can easily get robust models now. And basically you can just look at these two lines here above, right? So we train an upper net now with a ConfNXT backbone, right? All these semantic segmentation models have typically an ImageNet type architecture as a backbone, and then some architecture around it which does the segmentation. And if you do adversarial training, for the standard training time they use in semantic segmentation for Pascal VOC, 50 epochs with 2 attack steps, you get absolutely or almost no robustness. But if you, and here you use the initialization with a normally trained model. Yeah, that's basically what typically is done in semantic segmentation. You initialize the backbone with an ImageNet model, and then you train just for semantic segmentation. But if you replace that now with a robust ImageNet model, then you can train with 50 steps already a highly competitive model, and it's even better than if you train with a clean initialization for 300 steps. Yeah, and this also generalizes to 5 steps. Just changing the initialization gives you much better robustness directly, and it's only slightly worse than if you train much longer with the clean initialization. Yeah, so and that shows basically that its robust ImageNet models are now, I think, can be used in a versatile fashion for a lot of tasks. Yeah, and not only for probably semantic segmentation. Okay, the next point is just a teaser for a poster we have here. It's about robustness of multimodal foundation models. I think that has also mentioned being in the previous talk. Basically, here we attack OpenFlamingo. OpenFlamingo has a vision encoder and which is basically a clip model, and then use a language model. Then it has some cross attention to bring this together, and then you can do image captioning. And compared to what has been shown in the previous talk, we have a different threat model. So we have a threat model where we assume that there exists a malicious third party which wants to manipulate users, right? For example, by spreading fake news or fraud. And so what you can do then is you can do a targeted L-infinity attack on image captioning. So you can manipulate this image with a basically imperceptible change, and then change basically the output of this imaging captioning model and basically to any output you want. And I think that this kind of subtle attacks on users are basically even more threatening than just attacking the foundation model directly. Okay, but if you want to know more about this, then please come to the poster session. Okay, in the second part of the talk, I want to speak about the good side of adversarial robustness. I mean, first of all, sometimes adversarial robustness helps, right? It's not always bad. Sometimes just training with a small threat model can actually even improve performance. At least there is a relation to sharpness-aware minimization, because sharpness-aware minimization, which should or is said to improve generalization, is motivated by adversarial robustness in weight space. And I always say there is hope, because the human visual system seems to be fairly robust, and it should be possible to achieve the same. But what I want to focus now in the following is the good properties, because adversarial robust models have, in contrast to normally trained models, a lot of nice properties. And the most important one is what I call the generative property. And this, I will explain it in a second. And this generative property can then be used for debugging of these models. Okay, so first of all, it has been noted early on that this is work by Matri and others here, that the gradients of robust models are much better behaved than of normally trained models, right? So you can get much better saliency maps, so GradCam works better for a robust model and so on. And then also it has been realized that you can do visual counterfactuals also with a robust model relatively easily, right? That was also a model paper by Matri's group, and we also worked in this area then later on. So in a visual counterfactual, basically you just ask the question, what is the minimal change to the image so that the classifier would decide for a different class? And in principle, we all know how to do that. It's just a targeted episodal attack, right? So we can just maximize the confidence of the model into the target class. And clearly, if you do that for a non-robust model, let's say you have this input image and you want to change the class from this kind of building structure to megalith. Clearly, for non-robust model, you get nothing. But for a robust model, you get a semantically meaningful change, right? The same happens here. If you, I think this was an image of a star formation in a galaxy. If you change that to jellyfish, you get a reasonable counterfactual. So these kind of things work nicely for a robust model, and I think this shows that these models have picked up actually a better understanding potentially than standard models. Now, how can one use that for debugging? Basically, you start with an image here, like from a class bubble, and you change it into B. Now, if you look at this image, you probably say, oh, there's a failure because I see on this image no B, right? So why does this the classifier now say 99% for B? Well, you see actually here on the side, there are some flower structures. And now the point is that in the training set, if you look at the training set of B in ImageNet, there are a lot of EBs which actually sit on large flowers, right? The B is actually only a minor part of the image. And so what the classifier has actually picked up is that flowers are actually a very important features for bees, and it generates them here. And our goal now, actually, and this is a paper here also at ICCV, was basically wanted to discover this kind of harmful spurious features. So and what are harmful spurious features? So a harmful spurious feature basically triggers the decision for a class without the class object being present. Yeah, so the spurious feature can actually be okay, right? So spurious features are per se no problem, right? Also, we as humans use a lot of context information to make our decisions, so that is not a problem. But if the spurious feature alone triggers the decision for the class, then it is a problem. Yeah, and just to show you some examples. Now, question would be, what are how would ImageNet classifier classify these images? And I tell you that fountain is a class in ImageNet. Okay, I guess you would expect that all ImageNet classifiers classify these images as fountain, but they classify them as fireboat, right? So why do they classify them as fireboat? Well, there is a large subpopulation in the fireboat class which contains this water jet feature, right? And basically, you see that you have also these water jet features here. Now, I can also ask you, how are these images classified? And graffiti is not a class in ImageNet. Well, these images are all classified as fright car. So why are they classified as fright car? Well, you probably have guessed it. If you look at the training images of fright car, they contain a lot of graffiti images on the fright cars. Okay, and basically one can then make a kind of taxonomy of where these harmful spurious features are coming from. So the first case would be this fireboat versus fountain. So here you have these two classes, and they share basically a feature, right? This water jet. And because this water jet probably appears a bit more often in the fireboat class, the classifier has associated this feature now with fireboat, and therefore classifies all the images or a lot of images in fountain which contain these water jet features now wrongly as fireboat. The other way is basically that you have, as we have in this graffiti, now a large subpopulation of the fright car training images contain these graffiti features. And then the classifier just says, oh, graffiti is basically a fright car, and extends that basically to out of distribution images, namely all graffiti images, and will classify them as fright car. And clearly this leads to very unexpected behavior of a classifier if you apply it in the real world. it is something we would like to get rid of. Okay, and how do we do this? We basically we try to find systematically these kind of subpopulations in the data, and we do that by a class-wise neural PCA. So what is this neural PCA? We take basically the penultimate features of the penultimate layer, then do a component-wise product with the weight vector corresponding to this class. And then we take all training images of this class and then just do PCA in this space. And then basically, if you have this vector here, you can also represent the logic of this class just by summing up basically all the features, all the components of this vector, which you can also write equally as a product of this vector with the all ones vector. Okay, so then you can represent the original representation in terms of this PCA basis. And then in order to get basically the contribution to the logic, you just have to take the inner product with this all ones vector. And then that's basically what we call then the neural PCA component associated to this PCA vector. And then you can basically decompose the logic of this class into the contributions of all these neural PCA components. The second thing is basically then we want to visualize each of these components. So what we do is basically we start with a gray image. So we start with a completely non-informative image and maximize this neural PCA component in the vicinity of this gray image. And then the question is basically, how do we then know that a neural PCA component really contains a harmful spurious feature? If this basically image, which is then generated, produces mainly the spurious feature, but not the class object, and this image is classified with high confidence as class K, then we are relatively sure that we have found a harmful spurious feature. And it's all clear that this is only possible, right, if you have an adversarial robust model, because otherwise these images which you generate are completely trivial, right? So this is basically where the good properties of adversarial robust models really matter. And here on the left, you see basically how that looks like now. These are the top 5 PCA components which we have found. These are the corresponding visualizations outgoing from a gray image. And you see basically on this component 1, 3, 4, 5, you basically see feature, sorry, I should have said this is for class hummingbird. So you basically see bird-like structures, but here, I guess everybody sees it, you don't see a bird. And if you look at the maximum activating training images of this component, these are the maximum activating training image for each component. These are the corresponding heat maps. Now this is GradCam, but not GradCam for the classifier, but applied to the corresponding neural PCA component. Then you see basically that the GradCam actually focuses on the bird feeder, but not on the bird anymore. And it generates basically this kind of bird feeder also as the feature visualization. And then basically a human has to go through all these PCA components and then classify this as harmful spurious feature. Okay, and this is basically, then we could do this for the full ImageNet data set and then find basically for all classes potentially harmful spurious features. I should say there was also an earlier work by ICCVw23, very nice. They did the same also for complete ImageNet, but they did it not in the, they did it neuron-wise, whereas basically we just look for directions in the feature space. We are not looking at individual neurons. And they had this visualization, which was basically outgoing from the maximum activating training image, which I think is basically not very useful because it just shows you what you know already. And here basically you show what the classifier has really done because you start from basically nothing. Okay, and then basically we want to validate this, and how do we do that? We have again here random training images from the class ImageNet. These are this spurious component which we have found, and now we find images in another data set named open image, which activate mainly this neural PCA component, and then check basically if for ImageNet models also. So normal ImageNet models also classify this as hummingbird. And it turns out basically that all these images which we find here are also classified as hummingbird by normal models. So this generalizes basically from the robust models to also normally trained models. And here maybe interestingly, it even overrides the decision for B, right? Because there are a lot of Bs here on this bird feeder, but it basically ignores them. So this is actually a strong spurious feature. Okay, so in total, we find actually more than 300 of these harmful spurious features for basically over about 200 ImageNet classes. And then the question basically is, how can one validate this quantitatively? And how can we check the dependency of a classifier on these harmful spurious features? And for that, we developed basically this spurious ImageNet data set for 100 selected spurious features which we found. And we collect basically images from open images by ranking them first according to this neural PCA component. And then basically, first ranking them and then selecting images which are at least classified by 2 out of these 4 models here as the corresponding class. And from these images, then we manually check them for images which contain just the spurious feature, but do not contain the class. Yeah, so we select just the images which do not contain the class, but only the spurious feature. And then the measure for basically checking the dependency of the classifier, we just use AOC. Yeah, because basically for the predicted probability for class K on the spurious ImageNet data set versus the validation set of that class for ImageNet. And clearly what we expect is that for the validation set where the class object is present on each image, the classifier should predict higher confidence versus all our images which do not contain any class object. Okay, so an AUC of 100% should be easily possible. Here are just examples from this data set. So this is always the ImageNet class. This is the corresponding spurious feature. So hard disk contains the spurious feature serial label. Snorkel basically contains a spurious feature, basically humans underwater. So this is basically sufficient to trigger then the classification for snorkel and so on. Yeah, this is also often twigs are spurious features for birds, right? Because on the images in the training sets, birds are sitting on twigs, and that's why twigs are alone already sufficient to trigger the decision. Now, next, once we have identified the spurious feature, the important question is, can we also find a fix for them? Can we mitigate them this, basically? And actually, for the initial robust classifier, it's super easy because we have already this decomposition into the neural PCA component. And if we have found that one corresponds to just a spurious feature, then we just set it to 0, right? That's basically it. It requires no retraining or labeling of training images. It's super simple. And the nice thing, it also transfers to arbitrary ImageNet classifier, because what we can do is we can just compute the features of the another classifier. And then in this feature space, we look for the maximum correlation, the direction of maximum correlation with our existing neural PCA component. And then we just also project this out from the classifier. Yeah? So it also requires no retraining or labeling of any data for any ImageNet classifier. And this is about basically then the results which you get. So these are some models, basically also state-of-the-art models. You see here their accuracy. Here you see the corresponding score of this of the mean AUC value. So our robust model has actually a pretty bad score. So that's also, we found the spurious feature for this model. But you see also that even normally trained models have still a large dependency on the spurious features. So the spurious features are not just properties of the robust model, but they really generalize it even to state-of-the-art models. And you should not be mistaken by an AUC score of seemingly high 92%, right? You have to see always 100% should be the goal, right? 92 is still bad. And an AUC of 1 also still means that you separate in confidence the decisions, but not that the classifier could still predict the class for all the images. Now, the interesting thing is our fix here, that's this column here. You see basically that for the normally trained classifier, it yields almost no change in accuracy, so it does not harm, but you always get an improvement in terms of the dependency of the spurious feature. So you can basically improve your classifier for free with this fix, and it does not hurt you in terms of accuracy. Okay, and with that, I'm basically more or less done. I think we are probably over time already, so I just skip the conclusions and just take questions. Thank you.
Just raise your hand. And
just one question. Your curiosity is on the first slide. How do you try to calculate version of cost this
Yeah, it's the question, what is the new version?
So like the old version, we were doing say point,
Yeah.
new version, software.
Okay. I think we took the version when we communicated, I guess, with you.
Yeah.
So I don't know which version that
I was
was.
just curious if they were given this.
Okay. I don't know. Sorry.
Thank you.
Another question? If not, let's thank the speaker again. Thank you. Yeah, pay collector. Zoom 分享了，好像 Zoom 还没有成功。All right, please allow me to introduce our fourth speaker of our workshop. Dr. Yinpeng is a postdoctoral researcher in the Department of Computer Science and Technology, Tsinghua University in China. He received his BE and PhD degrees from Tsinghua University in 2017 and 2022, advised by Professor Jun Zhu. His research interests include machine learning, deep learning, and especially the adversarial robustness of deep learning. Dr. Yinpeng has published over 40 papers in prestigious conferences and journals, including PAMI, ICCVw23, and Europe's. Dr. Dong, please take it away.
Hello, everyone. Thanks for the introduction. I'm very glad to be here and introduce our recent work on adversarial robustness in the 3D world. So the title of my talk is on robustness of vision models in the 3D world. Computer vision models and deep learning models lack robustness to adversarial examples. As we know, these adversarial examples are generated by adding very small perturbations to normal examples, but they can make a model to produce wrong predictions. Adversarial examples can also exist in the real world for road sign classification or face recognition, so they can lead to real-world threats to deep learning applications. There are also some works on studying adversarial attacks in the 3D space. For example, the famous 3D turtle from MIT. They generate the 3D turtle in the physical world, which can mislead deep learning models by taking photos from different conditions. And some other methods can also modify the shape of the 3D objects to make errors. There are some challenges for 3D attacks. Okay. There are some challenges for 3D attacks. The first one is the stability of the adversarial examples. So in the physical world, we usually want the adversarial examples to be robust to 3D variations, such as the viewing direction, lighting condition. And the second challenge is the naturalness of adversarial examples. Many adversarial examples are very noticeable in the real world. So we want to make these adversarial examples more natural and imperceptible. And the third challenge is the effectiveness of the adversarial examples. In practical applications, we usually want to fool black box deep learning models without any knowledge of the model parameters or gradient. So in this talk, I will cover some of the topics that these years. The first is the viewpoint robustness as invariance of visual recognition. So here we identify a new risk of computer vision models to viewpoint changes, and we propose attack and defense methods to study the viewpoint robustness. The second one is we develop some 3D attacks against real-world applications, including face recognition and autonomous driving. And the third one is the robustness of large-scale foundation models, as also mentioned by Professor Hein. So let's start. First, I will introduce the viewpoint robustness or invariance. It has long been recognized that human vision has a very strong ability to correctly recognize objects from different viewpoints. Therefore, it's natural to ask how about the robustness of computer vision models to viewpoint changes. Here we show two videos of car accidents of autonomous driving. We can see that the autonomous drive systems did not recognize the frontal trucks or cars that were flipped over, and consequently cause the traffic accidents. From these cases, we can see that the computer vision models do not generate well to different viewpoints of the objects, so that it causes misclassification or misdetection of the object, and consequently lead to the traffic accident. So the key problem is that we want to study the viewpoint robustness of computer vision models. So in our first week, we aim to develop an automatic way to find adversarial viewpoints of real-world 3D objects. As shown in this figure, for the first line, we show that the photo taken from some normal viewpoints that can be correctly predicted by the model. And if we generate the adversarial viewpoint and take the photo again, we can see that the image are misclassified by the classification models. However, generating adversarial viewpoints need to model real-world 3D objects with high fidelity. And motivated by the recent progress of neural renderer, we adopt NERFs in this work. NERF represents 3D objects by a continuous density and color field. It learns MLP networks, which takes the 3D position and the viewing direction as input, and it outputs the color and the density at this point. NERF also adopts volume rendering to render the color of a pixel in the image, so that it can synthesize photorealistic images from any viewpoint. So based on NERF, we can build a very simple pipeline to finding the adversarial viewpoint. Given multiple views of an object, we first train a NERF model of the object. And then we want to optimize the viewpoint parameters to generate the adversarial viewpoint. And in particular, we use a 6-dimensional parameter V to denote the viewpoint, including 3 rotation angles and 3 translation distance of the camera. And we given a specific parameter of the viewpoint, we can transform the camera position and render an image from the new camera pose. Based on the rendered image, we can then compute some classification laws and perform optimization with respect to the viewpoint parameter V by some adversarial attacks methods. However, there are still some challenges to address this problem. First is that although NERF can generate very realistic images from no viewpoint, there is still a relative gap between the real object and the neural representation. For example, as we show in this figure, we can see that the nerve rendered image is very similar to the real image, but as the logo of the computer, the rendered image have a difference from the original logo, so that it's hard to it will lead to the problem that we do not know whether the difference between the rendering and or the viewpoint itself that lead to the wrong misclassification of the object. And the second challenge is that it's very hard to control the real camera pulse in the physical world to match the adversarial viewpoint found in the digital world. So to address this problem, we propose a method called viewful. It learns a distribution of adversarial viewpoint instead of only optimizing a single adversarial viewpoint in the 3D space. So the optimization problem becomes that we want to maximize the loss function of a classification model under the adversarial viewpoint distribution PV. And we also add a regularization term is the entropy of the distribution to avoid the degeneration problem. So by learning a distribution of adversarial viewpoint, they have some advantages. First is that we can better explore the search space, and the second is that we can better handle the fluctuation of the camera pulse because we learn a wide range of adversarial viewpoint rather than a single one. And the third is that it can mitigate the reality gap of the adversarial viewpoint, and it also demonstrates better cross-modal transferability. And in this work, we simply parameterize the adversarial viewpoint distribution by Gaussian distribution. In particular, we define a random variable U from a Gaussian distribution parameterized by the mean, mu, and the variance sigma. And we take the transformation of variable approach to normalize the random variable to get the viewpoint V. So under the Gaussian distribution, our problem becomes that we want to maximize the loss function under the Gaussian distribution, and our optimization target is to maximize the loss function with respect to the parameters of Gaussian distribution mu and sigma. To solve this problem, we can adopt some common tricks, such as the reparameterization trick. We can reparameterize U as equals to mu plus sigma dot epsilon, where epsilon is sampled from a standard Gaussian distribution. So by this trick, we can directly calculate the gradient of the loss function with respect to the distribution parameters and solve the problem. However, it can see that directly calculate the gradient of the objective function need very high memory cost. This is because we need to render the image by a nerve model, so that we need to store the nerve model for every pixel. So it's very memory intensive. So to address this problem, we adopt some black box attack method to optimize the objective. We simply adopt the common natural evolution strategy, which is commonly studied in query-based adversarial attack to solve the optimization problem. And the gradient can be approximated by the search gradient, which equals to the loss function as the point produced by the gradient of the log density of the search distribution. So based on natural evolution strategy, we can obtain the final gradient of the loss function. Here we show some experiments. First we conduct digital experiment. We collected 100 3D models, and we use our method to attack some common image classifiers. We can see that we can achieve very high attack success rate. It is more than 19% attack success rate against these models. It should also be noted that we didn't change the texture or the shape of the 3D object. We just take them from different viewpoints. Here we show some visualization results. The first line shows the real image taken from some common viewpoint, and the second row shows the rendered image from the adversarial viewpoint, and the third row shows the real image taken from the adversarial viewpoint. We can see that the images from the adversarial viewpoint can mislead the model, and it also should be noted that for some examples, the real image from the adversarial viewpoint cannot attack the model successfully. For example, see the last column, we can see that the images between the rendered image and the real image is very similar, but it results in different predictions of the model. It is also, we think it's also an effect of the adversarial perturbations that cause the misclassification rather than the viewpoint. Here we show that the adversarial viewpoint has very high cross-model transferability. We generated the adversarial viewpoint for ResNet or VIT, and we show that they can transferable to attack other models. And we also conduct experiments in the real world. We train another model for the real world 3D object, and we use our method to generate the adversarial viewpoint. And we again take photos from the adversarial viewpoint in the physical world. It can be seen that although we cannot precisely match the adversarial viewpoint found in the digital space, the captured image can also mislead the model. Based on our method, we also established a benchmark called ImageNetV. It consists of 10,000 images of the adversarial viewpoint, and we use them to evaluate the robustness of ImageNet classifiers. Based on the result, we also found that transformer are more robust to viewpoint changes, and bigger models tend to perform better. And we also found that some adversarial training and 2D data augmentation techniques do not have good results under the 3D viewpoint changes. Okay, we have found that the visual recognition models are vulnerable to viewpoint changes. And next, we want to study how to achieve viewpoint invariance. We define viewpoint invariance of a function f as that its predictions under two different viewpoints should be the same. To achieve viewpoint invariance, we propose viewpoint invariant adversarial training method, motivated by the success of adversarial training to defend against LP non-bounded adversarial examples. There are still some challenges to perform adversarial training to achieve viewpoint robustness. The first, that it's hard to acquire high quality training data because we need 3D models rather than the 2D images. And to address this, we make a great effort to collect a new data set containing 1,000 synthetic 3D objects of 100 classes of ImageNet. And the second challenge is how to capture diverse adversarial viewpoint to prevent overfitting of adversarial training, as we know that adversarial training often has the robust overfitting problem. And we propose a new attack which can characterize more diverse adversarial viewpoint using a Gaussian mixture distribution. And third one is how to enhance the training efficiency, because if we want to generate the adversarial viewpoint for an object, it requires much computation time to optimize the viewpoint parameters. Our proposed viewpoint invariant adversarial training can be formulated as a distribution-based minimax optimization problem. The problem is very similar to ViewFu. The inner maximization problem aims to learn a distribution of adversarial viewpoint, and the outer minimization problem trains model parameters to under the worst case adversarial viewpoint distributions. And for the inner problem, we could adopt ViewFu as a practical solution, but ViewFu only learns a single Gaussian distribution, which cannot capture the diverse adversarial viewpoint in the 3D space. So in this work, we propose a new attack called GMVFu, which learns a Gaussian mixture distribution. And the problem formulation is very similar to willful, and I will skip these details. So by adopting a Gaussian mixture distribution, we hope that it can characterize multiple local maxima of the viewpoint, adversarial viewpoint, and improve the diversity of the adversarial viewpoint to mitigate overfitting of adversarial training. For the outer minimization problem, we improve the efficiency of training by some strategies. The first one is the stochastic update strategy. This strategy means that we only update the viewpoint distribution parameters for only one object in each category during training, and we keep the distribution of other objects the same. And the second strategy to avoid overfitting is the distribution sharing strategy. It means that we during adversarial training, we use the adversarial viewpoint distribution optimized for itself or other object among the same category for training. Here we show some results. We conduct experiments on ImageNet and our collected IM3D data sets, and we compare our method with some baseline method, including some random augmentation methods, and we can see that our method can improve the viewpoint invariance over these baselines. Here we also show that the generated adversarial viewpoint compared with willful. Since our new proposed GM willful can characterize a Gaussian mixture distribution, the adversarial viewpoint exhibit much diversity than the willful. And based on our newly proposed GM willful, we also established ImageNet V plus benchmark. It is much larger than ImageNet V. It contains 100,000 images of different objects, and it has better diversity. It contains 1,000 objects with 100 classes. And we also use the ImageNet V plus benchmark to evaluate the robustness of large-scale vision language models, especially the CLIP model. As shown in the original CLIP paper, the CLIP model show very good robustness to out-of-distribution data. It can be seen that the zero-shot performance of CLIP is much better than the supervisory trained ResNet to out-of-distribution data, and the gap between the in-distribution and out-of-distribution data is very similar. Here we evaluate the robustness of these vision language models under our viewpoint changes. We can see that these large models, including CLIP, have the performance of these models drops significantly under the viewpoint changes. It shows that these large-scale models are not robust under 3D viewpoint changes, and it would be more dangerous for real-world applications. Here we summarize these two works. We study the viewpoint robustness of computer vision models by proposing two methods, and we adopt a distribution-based modeling approach to find diverse adversarial viewpoint in the 3D space. And we think that the distribution-based approach can be used for other attack settings. And we also established two viewpoint robustness benchmarks, ImageNet V and the ImageNet V plus for robustness evaluation, and our code is available. And next, I will briefly introduce our 3D attack against real-world applications. Here we show the 3D attacks against face recognition. There are a lot of previous works on face attacks, which mainly consider 2D face patches, and we study 3D face attacks. It has some advantages over the 2D attacks. The advantage is that they are more fitting to human faces, and they can be more natural and imperceptible, and cannot be easily detected by some defense mechanisms like face anti-spoofing. And they are more stable under 3D variations. And so in this paper published at CVPR, we propose an effective 3D face attack. And in this work, we represent face by 3D morphable model. which models the 3D face by low-dimensional coefficients, including the shape, texture, and others. And we perform optimization in the low-dimensional space of 3D such that the face mask generated can be more natural and transferable. And I will skip the details of this model. Here we show some results and demos of our attacks. With the 3D adversary mask, we can invade many commercial face recognition systems, and the overall attack success rate is higher than 15%. In autonomous driving, we also study 3D attacks and propose a 3D consistent patch attack. The main difference is that for attacking autonomous driving systems, we need to consider the temporal consistency, such that we need the adversarial patches to consistently mislead the model at a different time. And we use 3D bounding box to locate the corners of the patch in the 3D space, and we optimize the patch to be spatial and temporal consistent. And we also establish robustness benchmark in autonomous driving. And our goal is to evaluate the robustness of 3D object detection models to some advanced weather sensor noises in autonomous driving. And we synthesize these corruptions on typical benchmarks in autonomous driving, including KT, nuisance, and Waymo. And we also conduct large-scale experiments on many diverse 3D object detection models to evaluate their robustness. At last, I want to share one of our recent works on attacking large-scale foundation models. Multimodal large language models is very popular recently, which usually extract image features from an image encoder and then learn some projection layers to align the image embedding and the token embedding. Which is as the input to the following large language model to output some descriptions. So these multimodal large language models, and especially some commercial models, including GPT-4 and BART, show very strong abilities in vision-related tasks such as image description, visual question answering, visual reasoning. However, the introducing of this image as input can also provide an appealing attack surface due to the continuous nature of images. We can add adversarial perturbations to the image and cause the large language model to output wrong predictions. Here we show a recent work of us to attack the black box model of Google BART. In this paper, we designed two attack objectives. The first one is the image embedding attack. We want the image features of the original example and the adversarial example to be far from each other. And the second one is the text description attack. We directly attack the output description of the large language model to match a target sentence. And to optimize these objectives with high cross-model transferability, we adopt a method called common weakness attack, which is a recent method proposed by us to attack an ensemble of models by using their common weakness. And for surrounded models, we adopt CLIP, BLIP2, and WEIGHT. For the image embedding attack, we also adopt BLIP2, Instruct, BLIP, and mini-GPT-4 for the text description attack. Here we show some results against the commercial models. Here's the results of BART. We show that by adding very small perturbations to the images, the BART can output significantly wrong predictions. For example, the panda face is misdescribed as a woman face. And overall, we can achieve 22% attack success rate against Google BART. We also try other commercial models, including the Bing Chat, and we use the same adversarial examples to evaluate the robustness of Bing Chat. And overall, we achieved 26% attack success rate against Bing Chat. And the same image, the panda face, is misclassified as a cat face. And And for evaluating the robustness of BART, we also found that BART have some defense mechanisms. We found two defenses of BART. The first one is face detection. It cannot predict for face images. And the second one is toxicity detection. It cannot predict for the toxic images. And we show that these two defenses can also be easily attacked by our attack method. We can see that by adding some perturbations to the adversary, to the face image, BART can output the description for this image and also the identity of the person in the image. And also for the toxic images, it can also provide a correct description of the image. So it can also cause some safety problems of using these large language models. Okay, thank you for listening.
We have some questions from the audience. Just raise your hand. We have a mic on there. Yeah, there's a question.
Hi, thanks for the interesting talk. I was wondering for the attacks on the real bar, what radius for the framework you use, and how does the success of the attack happen?
Okay, we use a standard setting. We use the L infinity perturbations with the perturbation batches 16 of the pixel value ranging from 0 to 255. Right.
Is there another question? Comment.
Hello. Thank you for the great talk. I have a question about the viewport. So yeah, in begins the viewpoint of the video object. Sometimes the human itself may be difficult in understanding what the object is because like some of the are missing. So how do you think about that kind of situation in the other?
Okay, thank you for the question. It's true that some objects from the adversarial point are not very noticeable for humans, even for humans to recognize. For example, the street sign we from the adversarial point is very small and we may miss it. And our goal here is that we can find the adversarial point for some objects that is also recognizable for us. For example, the chair in the image, and we show that the chair from the top view can also be misclassified. And from our experience, for some simple objects, indoor objects, very simple, we can find the adversarial point such that the images are very recognizable by humans. And for outdoor scenes, especially for some street signs or some others, the background is very complex, and the generated adversarial viewpoint is maybe very hard for people to recognize. And we think it may be due to the our method itself. Maybe that we adopt that the very simple nerve method to model the object. We could adopt some advanced nerve method that can build a 3D model for outdoor scenes with very high fidelity. We hope that we think that it may address this problem.
Is there further questions? If not, let's thank the speaker again. Thank you, Dr. Dolan. So this marks the end of the live session. Good morning. We have photo session right now. Now after the session restarts at 1:30.
今天下午需要帮忙吗？
应该还好。对，
那我走
对
了，那我去
好
听歌了，拜。
啊，拜拜。
哎，那我就订5号了，回来找你做。
对，5号我们是下午2点，
这都是谁？是你跟刚才那个？
就我跟韦老师定了。
行行，那
对
我就回去找你。
好，
拜拜。
拜拜。 Hi, Professor Wang, can you hear me?
Hello? Yeah, I can hear you.
Can you share
Can you
your?
hear me?
Yes, I can hear you.
Yeah.
Can you share your screen?
Okay.
Hello?
Does it work?
Yes, I can see it. Please, wait 2 minutes. Okay. Hello, everyone. Welcome to the afternoon section. In this afternoon, we have another 4 speakers. The first speaker is Professor Liwei Wang. Liwei Wang is a professor in the Department of Machine Intelligence, Peking University. His research interest is machine learning. Let's welcome Professor Liwei Wang for the presentation.
Hello? Yeah, thanks for the invitation. So today I'm going to talk about robust generalization, and I'm going to look about it from a theoretical point of view. So what is adversarial robustness? So for adversarial example, we have a normal image, which is on the left, and we add to the normal image adversarial perturbation, which looks like the one in the middle, but we typically multiply it with its small coefficient. And this results in an image in the right. And this image in the right, which looks like nothing but a panda, however, it's usually misclassified by a deep neural network as given with very high probability of confidence. So what's the point? Why does it comes with this image which looks like panda by human but misclassified by neural networks? This is because the perturbation, so this noisy like perturbation image, it's not a noise. It's carefully computed by using some algorithm to find this perturbation so that to make the image perturbed image misclassified by the deep neural network. Okay, so the adversarial robustness problem has been discovered almost a decade ago. There are many algorithms and efforts have been proposed to solve this problem. But so far, this problem, the adversarial robustness problem, has not been fully solved. But actually, the adversarial robustness problem is quite simple. We can formalize this problem as a simple min-max problem. We just ask for each data point. It's not only be correctly correctly classified, but also the neighborhood of this data point is also correctly classified. Okay, so this is a simple formulation of adversarial robustness. Before we talk about anything about robust generalization, I want to mention this table. So let's look at the problem we are facing in the robust adversarial robustness. The big issue in adversarial robustness is the robust generalization gap is very large. For example, in the right column in this table, we see when we use adversarial training algorithm, we can get a very high robust training accuracy. So here we get 100% robust training accuracy. However, for robust test accuracy, it drops a lot. We have only like 50% robust test accuracy. So there's a big gap for robust generalization. And this is in sharp contrast with standard generalization gap. For standard generalization, we always have a good standard training accuracy and a good standard test accuracy. So for standard generalization, the gap is typically small, but for robust generalization, the gap is typically very large. So this is the key issue we are facing in robust adversarial robustness. So the question we ask in this talk is, why is robust generalization in deep learning is difficult? We try to provide some theoretical understanding of this phenomenon, and we try to answer this problem by introducing the factor that the size of the neural network matters here. So here is the one slide take-home message of my talk. So in this talk, we will show that the size of the neural network, that is the number of parameters of the neural network, actually have significant impact on the robust generalization gap. So here, let's see this table. It's a summarization of all the results of my talk. If we only consider robust training, if we want to have a robust training accuracy, the number of parameters of the neural network is just slightly overparameterized. Okay, it's a mildly overparameterized neural network is sufficient. However, if we consider robust generalization, so the goal here is to have a good robust test accuracy. For this purpose, we have to use a very large neural network. We have upper bounds and lower bounds of the size of the neural network, and they both are exponential in the data dimension. So here's the take-home message. We'll get into the details soon. Okay. Before we talk about the details, I would like to mention something. I think it's a folklore in this area. That is the distance between the data from distance classes are actually quite large. I mean, the data from different classes are far apart from each other. It's actually far larger than the adversarial perturbation we typically use in our adversarial robust experiments. So let's look at this table. The middle and the right columns are the distance I calculated in these commonly used data sets between the data from different classes. Actually, it's a minimum distance from the data from different classes. It's a minimum distance, the between class distance, okay? And you can see that typically this minimum between class distance is an order of magnitude larger than the adversarial perturbation typically used in our experiments. So this adversarial perturbation is also called robust radius. So from this table, this simple result, we can see that the data are well apart from each other. So there must exist a lot of robust neural networks, a lot of robust classifier that can achieve both good training, robust accuracy, and robust test accuracy. So the problem is what these robust classifier look like and how do we find it, okay? So in the rest of this talk, I will always assume the data are well separated. So I will use these formulas that we assume there are two sets. So basically we consider binary classification. There are only two classes, and A and B represent the set for the two classes. If we think about, if we discuss training, then A and B represent the data points of each class. And when we talk about generalization or test error, so A and B represent the support set of the data distribution. So for each class, we have a data distribution, probability distribution, and A and B, when we talk about the generalization, they are the support set of the probability distribution. So we always assume these two sets, A, B, they have a distance between them, okay? So once there are a distance between A and B, for example, we always assume A and B has a distance 2 epsilon, okay? Then we can actually write down a formula for the robust classifier, simply like this, okay? And if we use a picture, you can see if we have one set represented by the blue points and another set represented by the brown point, then this curve, this solid curve is the robust classifier, okay, defined like this. So the existence of a robust classifier is ensured by the separation assumption, okay? So now let's look into the first question. First problem is robust training. So when we focus on robust training, when our goal is to achieve good robust training accuracy, so what about the classifier look like, okay? And we will confine ourselves to the deep neural networks. Actually, I will assume we use a fully connected neural network with ReLU as the activation function. Actually, these details don't matter. We can actually modify the architecture of the neural network and doesn't affect our results. So here we assume for training, we have two data sets, each for class, and they are 2 epsilon separated. And here is the definition of robust training error. This is the standard definition, okay? And here, delta is the adversarial perturbation radius, okay? So our first result is the upper bound for the size of neural network to achieve good, robust training accuracy. So basically, here is the upper bound. Basically, the upper bound, if we ignore the log terms, it's n times d. So n is the number of training data, and d is the data dimension. So this upper bound states that if you have a neural network that the number of parameters of the neural network is n times d, then it's large enough to guarantee a robust classifier. So let me explain the upper bound in more detail. What does the upper bound mean? It means that for any learning problems, the two sets of data points are 2 epsilon separated. Then there must exist a ReLU network with this amount of parameters. That is robust. It will achieve 0 robust training error, okay? So this is a the upper bound is a guarantee that for any learning problem, this amount of parameters is sufficient to represent a robust classifier on these training data. Okay, so this is the upper bound. So next, let's look at the lower bound result. So again, we are talking about robust training. Our goal is to achieve robust training accuracy. So what's the lower bound for the neural network? The lower bound is square root of ND. Okay, again, we ignore some logarithm terms. So how to interpret this lower bound? The lower bound means that there are some learning problems, two sets of data, training data. They are two epsilon separated. If you want to achieve a good, robust training accuracy, you have to use a neural network with at least this number of parameters. Otherwise, if your neural network is smaller than that, it's not possible for the neural network to represent the robust classifier. It's not possible for any neural network smaller than this to have a good, robust training accuracy. So this is what upper bound and lower bound mean, okay? To summarize these two results for the robust training, these results state that mildly over-parameterized. It means that the number of parameters is slightly larger than the number of training data. Mildly over-parameterized neural network is sufficient to have low robust training error. So this is also quite true in our empirical observations. So after robust training, let's move on to talk about robust generalization. Okay. First, let's talk about the standard robust setting of robust generalization. Okay. Again, we are talking about well-separated data. This is the assumption we all assume in all this talk. But now let's remind you when we talk about generalization, we talk about two probability distribution, and we assume the support set of the two probability distribution are far apart. There's 2 epsilon distance between the two support sets. Okay, and here is the standard definition of robust test error, and our goal is to have a classifier, to have a deep neural network that this robust test error is as small as possible. Okay. So here is the first theoretical result for robust generalization. This is an upper bound for the size neural network. This time, the upper bound is exponential in data dimension D. Okay, so this is very different from what we have for robust training. For robust training, it's typically it's polynomial in all the parameters, but now it's exponential in the data dimension D. Again, this upper bound means that if you have a neural network of this size, it guarantees you that there is a neural network that is robust in terms of test accuracy, robust test accuracy. So here we can guarantee the robust test accuracy is 0 once you have this amount of parameters. Okay. And the next result is lower bound. Again, the lower bound is exponential in D. The lower bound is not much smaller than the upper bound. Okay. So again, the interpretation of the lower bound means that there are learning problems. We have two probability distributions of the data, and the support set are well apart, are separated by 2 epsilon. However, if you use random neural networks whose number of parameters is smaller than this, then it is not possible to have robust classifier. It is not possible to have robust test accuracy, 0, okay? So it's a representation problem. If you use a small neural network, it's not possible to represent the robust classifier, okay, for this learning problem. So to sum up the results we had so far, these results say that there's a big gap between robust training and robust generalization. Robust generalization requires a much larger neural network than robust training. You have to use an exponentially large neural network. It has exponentially many parameters to represent the robust classifier for tests for generalization. Okay, so there's a big gap between them. Okay, so this in a first, so I think some audience might ask the question, okay, what you just get, the results you just get, looks like a worst case analysis result. The lower bound only rule out the possibility for a small neural networks for certain learning problems. So does this worst case analysis result really matter for our empirical, for our practical problems? So next, in the next session, let's look at some more practical scenarios. We assume, in addition to there is a 2 epsilon distance between the two classes, we assume that the data, the probability distribution, have a nicer structure. By nicer, I mean it's very easy to classify these two classes in the sense of a standard classification. So here, I assume the two classes are linear separable. So just like this picture illustrates, this class and this class can be linear separated, okay? And the distance, the linear distance between these two sets A and B is at least 2 epsilon. In this case, the standard classification is so easy. Let's see how difficult the adversarial robustness is for generalization. Okay. So here, this theorem is the main theorem of this talk. It's a lower bound for the size of the neural network in the linear separable case for robust generalization. So let me translate this complicated mathematical language into plain English. It says, basically, the lower bound is still exponential in the data dimension D, okay? Here, if you use a neural network whose number of parameters is smaller than this, then there will exist a universal constant so that the robust test error will be always larger than this constant. It can never approaches to 0. It's always larger than this constant. Okay, so this theorem tells us, even in this very simple scenario, the data linear separable, still we need very large neural network to have a robust test accuracy, to have a very good robust accuracy. If you use a small neural network, it's not possible to represent the robust classifier. Okay, so let me share some insights of this theorem. I'm not able to get into the detail of the proof, but actually the proof provides some insights. So why the standard classification in this setting is so simple? There was a linear classifier that can achieve 100% test accuracy. But for robust test accuracy, if you want to have a good robust test accuracy, you have to use this amount of parameters in the neural network. Why? Why they are so different? The insight is for robust test accuracy. If you want to have a robust classifier, the decision boundary of this robust classifier is very complicated by the definition of robust accuracy, by the definition of robustness, by the adversarial robustness. Okay, so because the decision boundary is very complicated, it's not possible to use a small neural network to represent the decision boundary. You have to use a very large neural network, this amount of parameters, to represent the robust classifier. So this is the insight. Okay. All right, so I think the results so far are pretty negative. Let's look at the a final setting. Okay, so in this setting, we make another assumption, which is often assumed for the learning problems of practical interest, which is the low-dimensional manifold assumption. So in this case, we assume the data are distributed in the low-dimensional manifold instead of in the high-dimensional ambient space. Okay, so we assume the dimension of this manifold is k instead of the ambient the dimension d. So we can have such an upper bound. In this upper bound, but actually it's as expected, this upper bound is almost independent of the ambient dimension d. It only depends on the intrinsic dimension k, okay? However, this bound is still exponential in the dimension k, the dimension of the manifold. This is the upper bound. Similarly, we have a lower bound. The lower bound is still exponential in the in k, the dimension of the manifold. So to summarize, in this case, the low dimension manifold case, we have some improved results. If the manifold is of very low dimension, then we can have a small, relatively small neural network that have good, robust accuracy, both in training and generation. Okay. However, if the manifold is not so low dimension, still this is a huge number. We still need a very large neural network to have good, robust generation. Okay, so to conclude, now we look at this table again. We can very clearly to compare all the results. For robust training, actually, neural network whose number of parameters is linear in all these parameters is sufficient for getting good, robust training accuracy. However, for robust generalization, you have to use an exponentially large neural network. Even in the very simple case, the data, the two distributions are linear separable, you still need an exponentially large neural network to have robust test accuracy. Okay, so that's my talk, and you can find the paper on archive. And thanks for listening.
Okay, thanks, Professor Liwei Wang, for the wonderful talk. Are there any questions? Okay, I have one question for this work. As you mentioned that the robust generalization of deep learning requires exponentially large neural networks. So what's your opinion of using the recent large-scale foundation models to achieve robust generalization? And what are the challenges for for using these large-scale foundation models?
Yeah, very good question. I think the large model is the right way. Although this is my talk is a theoretical talk, all the results are theory. We have to make simplified assumptions. But actually, I'm inclined to believe the results. We really need very large models. So I think large models, large language models, and other large models.
Okay, thanks for the wonderful talk.
Can you hear me?
Thank you. Yeah, yes.
So the large models have a chance to achieve very good, robust generalization. And for the challenge, I only talk about in this talk the representation. So representation means there exists the existence of such neural networks, but I didn't mention about training. This is another story. I think the main challenge is training. How do you train? How do you develop the training algorithm to obtain a robust model? I think this is a big challenge.
Okay, thanks, Professor Wang.
Okay, thank you.
Okay, let's move to the next speaker. The next speaker is Tramer. Tramer is a research scientist at Meta AI. Previously worked at Apple as a deep learning engineer. He received his PhD and master degree from the Technical University of Munich. His research interests lies in the field of computer vision, adversarial machine learning, fairness, and robustness in AI. So welcome.
Good afternoon, everyone. I'm Sharon. I work at Meta currently. With the factor annotations. So what we do here is basically we have set of members, we show them what the class prototypes are, and we ask them like what is actually between the sample image in terms of its pose, brightness, if the object is small, or its background. We also ask annotators for justification in like one sentence justification, and we also ask them to provide the one-word differences. So our annotation sets includes 16 different human annotations for the vectors. One-word summaries. So when we do the analysis of the one-word summaries, we have seen that actually top 20 patterns are very related to our set of 16 factors. So action summaries are really matching the choice of the factors that we have in this data set. So how we are labeling it, basically, we take 3 prototype images and make them based on the ResNet, the ResNet confidence. We show these prototypes and we show also each validation images one by one to label. So for example, if you see the cow on sample image, you see that actually background might be a problem. A cow that presents in seed actually and not a like common view for the example that can actually obtain the data set. So we ask labelers what is different, and labels can say object is partially present, object is partially blocked by another object. And they provide a sentence saying cow in water at the beach, which is not very common. Or they could say one word or like a couple of words explanations, each paragraph. So what does this provide? In ImageNet, we have a validation set where we have classes that we can actually measure the performance per class. We have variations of ImageNets out of domain data sets. But in our data set, we actually provide also the factors which enriches the analysis and help us understand how we can actually further analyze the model failures. Beyond factors, we also provide one-word references for the next actually documentation much easier than the rest of the data sets. So, for example, more examples here in the artichoke, you can see that actually in the example in the right side, the pose is different and the background is different. Or like in sea lager, you see that the pose is different, the background is different, the safari and the red ball, like another object appears in the sea. So what happens if we have this information? So we can actually analyze where the models fail and why they fail and what factors models are failing. So if we had a perfect model, the dashed line will match the distribution of the performances across all factors. That means that they will basically lie on the dashed line. But you see that for most of the classes, for example, for shape, the model performance is drastically lower than the average model accuracy. So ImageNet can help reveal limitations of average accuracy, understand model bias in architectures, and also help us characterize which choices in architectures, learning paradigm, and data augmentation, realization, effective biases. So, if we follow the model biases, we will see that models with similar overall accuracies have very similar factor accuracy. So, actually, all models fail for same reason. In our analysis, we also show that more changing data helps, but the robustness in interventions like data augmentations do not actually change the results much. They don't have much. Model weaknesses usually coincide with labeling errors that might put up in the data sets as well. So all model types, as I mentioned, have comparable error ratio, and how we find the error is basically 1 minus the in the model divided by the 1 minus accuracy of the model itself. So if a model is robust, its error ratio should be smaller than 1 or equal to 1. It will be bigger than 1 actually. That means because it is not robust in the sector we have analyzed. So in the figure you will see a lot of conversions by the supervised methods on more data, supervised on image advantage, self-supervised on robust interventions, right? And in most of the scenarios, you see that for both region, subcategory, and texture, these models are not robust. So we can also do some sort of analysis that data augmentation help or do not help. So what we do is basically imagine we are taking drops from the image and we increase our crop ratio from something small to equal with the image size, and we measure the performance of the model for each factor. So basically measuring parallel shifts how much more or less likely a factor is actually with among the models with specifications. Augmentations can actually improve robustness, but it might sometimes spill over effects to unrelated factors, meaning that while trying to fix one problem, we are actually creating others. So in this, the first part of the presentation, we will discuss ImageNet X and habit measures, robustness, or like understand why models fail. In comparison to all other versions of ImageNet, we provide human level factor annotations on the full validated part of the training set. So in the next one, I will explain actually how we are annotating $3 with the same factor annotations and how we are actually measuring the model robustness across incomes and regions. So $3 data set is a collection of video and images where we pass all people numbers provided with all recordings and labels. So we extend the $3 of the factor annotations. So, and we also do the analysis on like the foundation models similar to Q or other ones. Of course, like in a similar way, we found that performance disparities are most associated with differences in actual texture, occlusion, and image writing. So what happens in this paper, we annotate 15K images that has been labeled with ImageNet, 21K taxonomy. On average, 3.2 factors per image are chosen by the annotators, and multiple related factors are the color and pattern. Across all incomes, all background and patterns are the most selected factors. Interestingly, 10% of images in the low-income buckets labeled with texture, which tells us it's actually 5 times more likely to be selected within the low income bucket with respect to the high income buckets. There might be labeling bias, so we would like to address that as well in these values. So regional perceptions could be a source of variation depending on the label's background. So we create a second annotation task with the images where the labelers displayed with the ground truth labels or original object label. Almost 80 annotators from 6 different countries from various regions labeled whether they agreed or disagreed with the object label. And then we compare the levels of disagreement between annotators from the region where the image was taken, source domain, source region, and annotators who were from other regions. And our observation is that in both scenarios, this agreement is what brings here that tells us actually that the background of the label is not really affect much, or like creative noise in this label scenario. So regional differences in label perception do not really constitute a significant source of variations. So we further provide some analysis to dive into like these failure cases. If actually performance based across incomes and geographies, and you can see that actually like for the low income areas, it doesn't really perform that. And this scenario actually repeats itself based on architectures and learning procedures, and model performance decreases for lower incomes with these regulations. So the classes that differ most across incomes suffer 3 times more accuracy compared to the classes that differ the least across incomes. So you can see that for the Africa region, for example, texture and occlusion are the most one of the most affecting factors for the piece performance. So to actually understand, if you could have a mitigation, what is actually improving model robustness, at least for that factor. So what we did basically, we use texture debalancing, meaning that we take images, we train the background by applying some style transfer methods, and we train the model, and we actually measure how the model got more robust to these factors for the texture. And you can see that actually basically performance across low income buckets and regions with lower performance for images with marked texture as a distinctive factors. For this data set, we created a dashboard so you can actually go online and check like what labels for what regions and what annotations we can provide. Next, I will introduce the data set actually designed in both for failures, but it has also used for robustness measurements. Here's the conversations version 2. It's a large content-driven data set to measure algorithm bias and robustness. It's a data set of videos of people with self-provided labels as well as a clear concept to be data for measuring robustness and fairness. Some background, I was part of AROW team that time, and the defect detection challenge was introduced, and for the defect detection, constantly more than 100,000 videos, and it was back in 2022. It was basically the recordings of the videos of participants in case of providing age, gender, and skin tone, not skin tone, age and gender. Since we had the original data, we decided to release the original data set with the provided labels, and we also annotated the skin tone and lighting conditions and videos for further analysis. And this first version of tailored conversations was released around 2021. But it was not complete. Why? These videos only were recorded in the US, they have many other categories that we might need to understand the model's experiences. Potentially, skin tone is not ideal as skin tone for darker skin people, and consent was limited on for evaluation. So to resolve this problem, we went ahead and designed a video one collected in 7 countries, involved 15 XFR partners with 25 privacy XFRs. We worked with 2 vendors. We collected more than 5,000 participant videos, totaling up around 26,000 videos. We provide 11 categories, 7 of them self-provided for annotated, in total of 16 plus attributes. To design this data set, so we want to understand what kind of categories actually we need to measure model robustness of fairness. We went ahead with some literature review and actually released this literature for researchers to understand how we chose the categories, how we decided subcategories. For example, gender can be defined in many ways. ACI defines gender with 5 ways, but you cannot have all the options for gender. So we did a lot of research understanding to what level we have to provide functions to participants release this paper. In comparison to version 1, you can see that geodiversity has increased. We provide more labels, more attributes and options. For example, gender is now defined as binary, like cis man, cis woman, trans, non-binary, and self-defined. For each video, we provide this rich set of labels that you can use for things, but labels for robustness, where we provide video quality, there's a background noise, what language is in what environment the videos were captured, whether it's rain, sunny, or other stuff. Just to show some distributions, we see that it's not a uniform distribution for genders. And this is kind of expected also because when we collect data and we actually content, we don't target the specific groups of people. That's and this would also in real life we would have more or less genders, a lot more than transgender population. In this data set, the first time Mikel was annotated, it's actually released by Tramer to the recruiter. And this data set is the first application of Mikel. So we provide both levels for perspective and more that we can show analysis as well. The data set is tightly a license agreement, but it's also a large download and use for model evaluation. Sharing, and you can see the data set characteristics on the right side will be the 7 self-provided and 4 annotated data set for the data set. So in talk, we have discussed the receipt data set with the conversion and how much we receive it. And now, if you have any questions, I would like to answer that. Thank you.
Okay, thanks for the wonderful talk. Are there any questions? Okay, I want to ask a quick question. You have done a lot of work on building robustness data sets to understand the robustness of the current models. So, do you have any idea on how to improve the robustness of these models? And what is this problem very hard to solve? And what are the challenges?
So I mean, in one of the examples for the image that we have seen, my colleagues, we have seen that texture bias might actually help to improve the model robustness for texture, but it might also create problems for other factors. So the problem of mitigation is that it's a multifold. So while we're trying to do something to break other things, to the extent we can measure in the capacity of annotations, there are ways to mitigate all the issues. But the danger is that we don't know what we actually get. So, and if you don't have the data set for that particular thing that you don't know how to measure, that we are breaking, it might actually create other problems.
Okay.
So it's a hard problem.
Okay. Okay, thank you. Any other question? Okay, let's thank Kenner for the wonderful talk again. Thank you. Hi, Florian, are you online? Can you hear me? Please unmute. We cannot hear you. Oh,
yeah,
okay.
All good. Can you hear me now?
Yeah, yes.
Perfect.
Please wait a minute. I'm setting up the computer.
Yeah, let me share my screen.
Okay, can you share your screen?
There we go. This is paused. Okay.
I will introduce our next speaker. Florian Tramer is an assistant professor of computer science at ETH Zurich. He leads the SPY lab and is a member of the Information Security Institute and of ZISC and associated faculty of the ETHC AI Center. His research interest lies in computer security, machine learning. In his current work, he studies the worst-case behavior of deep learning systems from an adversarial perspective to understand and mitigate long-term threats to the safety and privacy of users. Okay, you can start.
Yeah, thanks a lot for inviting me to give this talk, and sorry about not being able to attend in person this year. I actually changed the title of my talk slightly when making some final adjustments. So what I'll be talking about today here is about how we should think about machine learning systems when we study adversarial machine learning, when we study attacks and defenses on these models. And I'll give some examples from some recent work from my group and from other collaborators on sort of why I think that this view of sort of looking at machine learning systems is very helpful and kind of needed if we want to know how machine learning systems could be vulnerable in practice. So the starting point for this is that there's been a lot of work in this community that has really focused on attacking and defending machine learning models. So we kind of take the machine learning model really as the centric object of our study, and we've looked at things like data poisoning, adversarial examples, model stealing, data leakage, and so on. There's a whole bunch of attacks and defenses that people have studied, but really in this setting where we kind of assume that the machine learning model kind of lives in isolation. The problem is that this is not what people do in practice. No one just deploys a machine learning model. What people do instead is that they deploy machine learning systems where the machine learning model is just one small but very important, but still small part of a much larger system that performs data pre-processing, post-processing, monitoring, analysis, and so on and so forth. And so the question is, if we now look at this picture and we see sort of the things we've been focusing on is this kind of small machine learning blob in the middle, the question is like, what does all the rest of this picture mean for adversarial machine learning? And today I'm going to talk about two ways in which sort of studying the system level sort of changes a bit how we should think about attacks on machine learning models. In the first part, we'll see that evading such machine learning systems, so attacking them with adversarial examples, is actually quite a bit harder if you take the full system view into account, which is kind of what we should be doing because that's what people use in practice. And in the second part of the talk, I'll mention briefly some very recent work we did on new privacy attacks that machine learning systems introduced that sort of a machine learning model in isolation would not be vulnerable to. So first, as I mentioned, we'll be talking about evasion, so adversarial examples for machine learning systems. So I guess everyone here is familiar with adversarial examples that we can sort of perturb inputs to machine learning models to make them misclassify things. And here again, a lot of the work has kind of focused on sort of a bit of a, it's a bit of a toy setting. Okay, we have a cat that gets misclassified as guacamole. We don't really care about this in the real world. Sort of what we care about is that we have an actual system that uses, say, computer vision and is going to be under attack. So let's look at the real setting, a real threat model where these attacks could potentially be used for doing something to a real system. An example I like to use for this, because it's kind of nice to illustrate with images, is to post bad content online. So the threat model you can imagine here is that you have some online platform, like a social media platform, maybe like Twitter, where like this platform wants to prevent certain content from being uploaded, like maybe not safe for work content. And so what the platform is going to do is they're going to run some kind of machine learning classifier, some kind of vision model here on every image that gets uploaded to the system to sort of detect which things are bad and block them so that they don't get shown on the platform. And so this is, of course, a system that people will want to attack. Like there might be some people who want to post bad content or unwarranted content to the social media platform. And so they'll want to find a way to evade this machine learning system that performs this filtering. So the way this would look like is like this. They would take, say, the original image that they'd like to upload, which gets blocked. They would run some kind of attack to transform this image into one that bypasses the machine learning filter and gets posted to the platform in this sort of slightly perturbed manner. The goal here for the attacker is kind of twofold. One is to bypass the machine learning filter, but also to make sort of small changes to the input, because ultimately they want this content to be shown to the real human users of the platform. And so this is kind of a prime example where of a setting where adversarial examples would be sort of a good attack vector. So how would we do this against, say, a social media platform like Twitter? Well, we don't know exactly how this system works, what kind of machine learning model they might have deployed. So what we'd want to do here is something like a black box attack, like some kind of query-based attack, because all you can really do as an attacker is sort of upload something to Twitter or to another platform and sort of see whether it's blocked or not. And that's kind of the only bit of information you get. And so there are attacks that have been developed in this community that work very well in this setting. The way these attacks work is that you sort of start with an image that you want to upload to the platform. It gets blocked. Then you maybe add a whole bunch of noise to it so that it no longer gets blocked. But the attack is also, at this point, not particularly useful because the image is sort of so distorted that it's not particularly useful to post it online. And then you sort of iteratively try to reduce the amount of noise. Maybe here the picture gets blocked again. And then over time, you sort of optimize the amount of noise that you have to add to the input so that you get an adversarial example, so that the input that you now have has a very, very small perturbation, but it fools the machine learning filter and so it gets posted to the platform. So this is sort of at the very high level how black box attacks, sort of query-based attacks could work in such a setting to sort of circumvent an online content filter. And as I said, there's been a lot of work on these type of attacks, on making them very, very efficient over time. And there's been sort of multiple papers written sort of trying to improve these attacks. Here are just some representative numbers on a bunch of different attacks that try to minimize either L2 or L infinity perturbations on, this is for ImageNet. The point here is that these attacks have improved quite a bit over time. What I mean by improvement here, or kind of the way that the field has measured improvement for these attacks, is by essentially checking how many times you have to query the machine learning model in order for the attack to be successful. So kind of in every step of the attack, you sort of send a picture to, say, to Twitter, and Twitter either blocks or doesn't block your image. And this sort of gives you some signal that you can use for your attack. And so, of course, you want to minimize the number of queries you make to the system, because, I mean, this would involve, say, making a network request, sending something to the service, and so on. What we argue, and this is in a recent paper with my student Eduardo De Benedetti and with Nicholas Carlini at Google DeepMind, what we argue there is that this metric of total queries made to a machine learning model is not really the right way to think about this. And that sort of, if you have a machine learning model that's kind of in isolation, there's sort of nothing around it, all you're doing is sort of attacking a machine learning model, it might make sense to think about sort of how many times are you querying this thing. But if you're thinking about a full machine learning system, there's a lot more cost considerations that have to be taken into account. The main reason is that a real sort of security sensitive machine learning system, like an online content moderation system, will use some at least basic form of monitoring. And this is obvious on a social media platform, right? That so if you upload content that the platform doesn't like, so the machine learning filter kicks in, the content gets blocked. But that's not all that happens. Like in the background somewhere, in some database, your IP will be logged as like, this person is doing bad stuff. And if you do this too many times, your account is going to get blocked, your IP address might be banned. And so there's a whole bunch of sort of extra costs that come from queries to the system that the system actually flags as being bad. So if we look at sort of the simple attack I was showing earlier, where we sort of query the model while sort of changing the amount of noise, and some of these queries pass the filter and some of them don't, not all of these queries are going to incur the same cost to the attacker. Essentially, if you post a picture to, say, to Twitter, and the machine learning filter doesn't kick in and the picture gets posted, there's very, very little cost to the attacker in doing this. I mean, you have to pay for the network bandwidth, I guess, to do this, and there's some amount of time that this takes, but that's about it. Whereas when you post something that gets blocked by the system and you sort of do this too many times, your account gets banned, and then you have to sort of create, a new account, a new email address, depending, maybe you might want this attack to work from a premium account on Twitter, and so you'd have to pay a new subscription. And so creating new accounts is an expensive procedure. And so every time sort of your attack gets flagged and your account gets banned, the sort of an order of magnitude higher cost to the attacker. And so there's really an asymmetry here between the type of queries that you make. Some queries are very, very cheap, and so we shouldn't really care too much if we're going to make a lot of those. And then some queries in comparison are incredibly expensive, because they sort of kick in some monitoring system that takes sort of extra actions to penalize the attacker. So given this asymmetry of query costs, what we suggest is that instead, these black box attacks should strive to be stealthy. And what that means is that, as before, what our goal should be is to find a way to perturb some input to the system so that it gets misclassified, so that we can kind of bypass the content moderation filter. But we don't want to do this while minimizing the number of queries sort of overall. What we really want to minimize is the number of alerts, sort of the number of times that our queries are going to get flagged by the system. So essentially, that means minimizing the number of times that we're going to post a picture or try to post a picture to Twitter, and Twitter's algorithm says, oh no, this is something bad, don't post this, and sort of flag the user. So the way we do this, the way we design such attacks is to essentially try to ensure that as we do this kind of optimization process, this black box optimization process, we try to ensure that most of the queries that the attack makes sort of stay on the good side of the model's decision boundary. So essentially everything that we upload to the service, we try to ensure that the service thinks this is fine. This is not something that should be blocked. And so pictorially, this looks a little bit like this. So on the left, you'd have what a sort of standard black box attack would do. This is a bit like what I illustrated earlier in my talk, where you do one query that has very little noise, and that gets flagged. Then you do one with a lot of noise, and you sort of do this kind of binary search for the amount of noise. And so kind of on average, you'd expect maybe half of the queries that you make to the system to get stuck in the filter and to be flagged as being bad. And so very, very quickly, with this kind of attack strategy, you'd expect that your attack would be detected, or at least your account would get banned. And so what we try to do instead is what is shown on the picture on the right here, is to sort of do an optimization attack that kind of tries to stay on the good side of the decision boundary, sort of try to always have an adversarial example, so something that fools the model, but where the perturbation is maybe relatively large, and we sort of gradually shrink the size of the perturbation, also trying to maintain the fact that we always sort of stay on the side of the boundary where the model thinks, okay, this is good content, and so the attacker doesn't get penalized. I won't go sort of into the technicalities of how we do this. There's sort of an interesting inspiration for the attack techniques we use here, which come from a famous sort of interview brain teaser called the egg dropping puzzle, which essentially asks to find the sort of maximal height, or the maximal floor of a building from which you can drop an egg without it breaking. To sort of do this while minimizing the number of times that you're going to break an egg in the process. So it's kind of a fun interview puzzles to sort of learn about different search strategies, about dynamic programming, and so on. And this is actually exactly the type of techniques that we use to create attack strategies that essentially try to minimize the number of times that we sort of fall on the wrong side of the model's decision boundary. And if you're interested in sort of the technical details of how we do this, I invite you to look at our paper, which you can find online. So how well do we do with this? So essentially on the good side, what we can do is essentially take any black box attack that's been developed over the years and sort of modify the way that it does optimization to sort of try to make sure that most of the queries that the attack does are going to be good rather than bad. And this works sort of across the board for many different types of attacks that we tried. So here are a few illustrative examples. This is the opt, sign opt, and hop, skip, jump attacks that have been developed over the years. And what we can do is sort of reach the same type of adversarial perturbation, so we can reduce the size of the adversarial perturbation similarly to the original attack, but while making sort of roughly at least 2 times fewer bad queries until the attack succeeds. So that's kind of the good part. The kind of slight downside to this, and this is kind of apparent from this picture here, is that the total number of queries we have to do to the system before our attack succeeds is quite a bit larger. And so whether this trade-off makes sense or not ultimately really comes down to this asymmetry in query costs. If you are in a setting where any query that sort of gets flagged by the system is way more expensive than just a random honest query to the system, then our techniques will give you a better attack. If you're in a setting where sort of these bad queries that get flagged by the system are sort of slightly more expensive, then probably the techniques we develop are not actually going to give you a better attack overall, because the total number of queries that we make is a lot larger. And so I think there's a lot of room here to actually improve these stealthy attacks. So to kind of try to drive some research on this question that we find quite cool, we created a benchmark you can find on GitHub, where we sort of want to have a leaderboard of black box attacks under this metric that we propose of sort of trying to minimize the number of bad queries that the attack makes. So just to recap what we saw in the first part of this talk is that essentially black box query-based attacks are actually not very practical when you take a sort of a full system level view, because we argue that sort of existing attacks optimize for the wrong metric, and that we really need to take the sort of monitoring component of a system into account, and we should strive to design attacks that are stealthy and that try to minimize the number of times that the monitoring system sort of kicks in. But optimizing this new metric that we propose is quite tricky, and this might ultimately require sort of fundamentally new ideas. So what we do in our paper is kind of try to retrofit existing attacks and sort of change the way they do the optimization to make them more stealthy. This works to some extent, but maybe we need sort of a completely new bottom-up approach to really design stealthy attacks. Okay, so this was sort of the first part of my talk on evasion attacks. Now, in the last few minutes, I'll just talk very briefly about what machine learning systems might mean for privacy. And here it turns out that sort of taking a system level view opens up sort of a huge can of worms of new attacks that had been sort of people hadn't really thought of so far. So what people had looked at so far and existing research was a lot like just looking at the type of leakage that comes directly from the model training process. So models tend to memorize some training data, and so after you've trained a model, some data will leak. You could do membership inference attacks, data extraction attacks, and so on. What we look at in a recent paper is sort of all the extra leakage that could come from extra components of a machine learning system, like data preprocessors or query filters and so on. And we actually find that these extra components could leak a huge amount of information. So just to give one example of such an attack, of such a leakage, we'll stay in the realm of black box of sort of query-based attacks, and we're going to look at one specific defense that people have proposed against these attacks. It's actually very, very promising, and so the type of thing you might expect a safety relevant machine learning system to implement. So what these defenses observe is quite simple, is that when you run these query-based attacks from the literature, they all end up doing many queries that are actually extremely similar to each other, because the way these attacks work is to essentially do some form of binary search to find the model's decision boundary or something like this. And so these attacks all end up making many queries that are all very, very similar to each other. And so the idea behind these defenses against query-based attacks is to just detect when a user is making many queries that are too similar to each other, and then just say, hey, there's an attack happening here, and then also just block the user. The problem with this, I mean, this is a very nice idea, but it's sort of very easy or relatively easy to circumvent this kind of detection through a Sybil attack. So just by creating the attacker could just create many different user accounts and sort of just parallelize their attack across many accounts. And so then you can't really detect that any user is doing anything fishy here, because the attack is kind of distributed across a bunch of benign looking users. And so the next step in these defenses then to sort of say, hey, this is the way we are going to detect whether such an attack is happening, is to just look at the global level, sort of across your entire user population. Are there many sort of similar queries that are happening? Is there like somewhere in your entire user base a fingerprint of a query-based attack. And so the way these defenses then work is to just keep kind of a log of all the queries that are being made to the system, and then sort of flag queries that are too similar to each other and block the users who made them. And this is, of course, pretty terrible from a privacy perspective, because it actually lets you sort of leak information about the queries made by other users of the system. And so this is one type of attack that we present in our paper, where we sort of have an honest user that's just making some sensitive query to a machine learning system, maybe to check their medical records. And then as an attacker, you can sort of exploit this this monitoring system to kind of just make a very, very similar query. And essentially, this will cause the monitoring system to kick in and to kind of raise an alert and maybe ban your account, only if a similar query has already been made by another user. And so you can sort of abuse this monitoring system to kind of learn something about the queries that other users of the system are making. So we call these privacy side channels, and this was just kind of one example of such an attack that we find and that we analyze. And our paper essentially explores many, many different such side channel attacks across kind of the entire data pipeline of a machine learning system. So we look at attacks in data pre-processing, like in deduplication pipelines. We look at data leakage in filters that try to prevent models from outputting memorized data. And we essentially show that kind of in combination, a bunch of these privacy side channels can even break sort of provable privacy guarantees of the machine learning model. Because again, here, essentially what our attacks exploit is the fact that we don't actually have a model in isolation. We have an entire system of extra components that each give sort of an extra surface of attack. So to conclude, I think the main takeaway I would like to give to you here is that we should study the security of machine learning systems and not just models kind of that are viewed in isolation. And this means that some of our attacks we might need to be revisited because they make unrealistic assumptions about what the machine learning system actually looks like. We saw an example of this with query-based attacks, where sort of the existing literature kind of assumes that every query to a machine learning model has kind of a fixed cost, which is not the case when you have a machine learning system with sort of additional monitoring components attached to it. And the counterpart to this is that additional system components can also bring a new attack surface that so far has been relatively underexplored. And so we looked at this from the perspective of privacy very recently and found that sort of many different components that people plug onto a sort of standard vanilla machine learning training and deployment pipeline sort of can cause data leakage in a variety of funny ways. And I think there's a lot more here to explore in how sort of real machine learning systems can sort of influence the way in which we attack or defend machine learning models. Thank you.
Okay, thanks for the wonderful talk. Are there any questions? Okay. You can go here. No mic.
Thank you very much for the talk. I just had a question about the realism of the attacks. So is it something that we need to define with the domain expert, or how do we design it, or is it just something that as machine learning expert have to come up with?
Yeah, thanks. So just to rephrase, so you're asking if we should be working with domain experts to kind of figure out which attacks are relevant, or sort of which assumptions on attacks are relevant, or whether we can sort of do this just as machine learning experts. So I think this is a wonderful question, and I would tend to agree that we should be working more closely with domain experts when studying sort of realistic attacks, and that especially when it comes to things like adversarial examples, evasion attacks. I think the way we study these attacks in sort of academic research is a little bit detached from the sort of real ways in which people attack machine learning systems, like content moderation filters, for example, that I talked about today. And so I think they're getting some a better understanding of how real attackers operate, sort of what kind of limitations they face or what kind of capabilities they have, would be very, very useful for sort of studying these attacks in a more realistic manner. Getting this information can be tricky because, of course, companies that actually deploy security-sensitive machine learning systems are not necessarily going to tell you too much about what kind of attacks they face on a day-to-day basis. But I think, yeah, having this conversation with domain experts is going to be necessary to make sure that the type of attacks and defenses that we study kind of map onto what real attacks look like.
Thank you. Any other questions? Okay, I have one question for the first work. You mentioned that you design stealthy query-based attack for black box models. So my question is, I see that you only consider the hard label setting, that's you compare with the some hard label attacks like a boundary attack. So my question is, how to design a stealthy black box attack for the query for the score-based setting. The previous method usually estimates the gradient to conduct the attacks.
Yeah, it's a great question. So indeed, we looked at the hard label setting where the system just sort of gives you a decision, which I think is the more relevant setting when it really comes to security, and that's kind of the first thing a security critical system should probably do is avoid leaking kind of confidence scores to attackers. There might be settings where such confidence scores are available just because they're needed by the application that's built on top of the model. And then you could try to design stealthy variants of those attacks as well. I think there you might even be able to, because you have sort of this extra information that comes from the confidence score, you could probably build attacks that are fully stealthy, that sort of never raise an alert during the whole attack. We actually tried to do some of these things early on in this project, but then kind of focused exclusively on the hard label setting. But I think it could be interesting to see how far you can push this in a score-based setting. Yeah.
Okay, thank you. And thanks for the wonderful talk. Okay.
Yeah, thanks everyone.
Our next speaker is Professor Yisen Wang. Okay. Yisen Wang is an assistant professor at Peking University. He obtained his PhD degree from the Department of Computer Science and Technology, Tsinghua University. His research interest is broadly the representation learning from various types of data. Specifically, we recently focused on theoretical and algorithmic approach for self-supervised, victim supervised learning, trustworthy machine learning, and graph as well.
Okay. It's for the inspiration.
Here is a picture of dog. So the systems will make a good prediction. It is a dog and make a very high confidence. And then if we give him another picture of dog, maybe you already know that this dog is different from the previous one. And the system will make the prediction of the death.
Can you share the screen on Zoom meeting?
So this is another picture of dog, and then it will make the prediction of the death. So we make the difference of the two pictures, and here we visualize the difference. You can see that most of them is blank. Have the number of 0, if 0 is used for the visualization, it is blank. So it means that the two pictures, actually their difference is very, very small, and sometimes human imperceptible. So the second picture is called the adversarial examples. So since the discovery of adversarial examples, many papers have rethinking the course of the adversarial examples. So here are some representatives like the local linear of neural networks, overfitting on finite samples, anti-random random noise, insufficient training data, and robust features, and also the contribution of matter in high dimension. So in this talk, we will focus on this about the robust and non-robust features. So let's first make a brief review of the robust and non-robust features. So here I'll given the training the image, and then we given adversarial trained encoder. Just here we need to give robust. Then we using the reconstruction method to minimize this objective to construct the data set. This data set is called the robust data set. Then for another kind of encoder, here is the natural trained encoder, we call it G very robust. Then we're still using the reconstruction objective to reconstruct the data set. Here is the non-robust data set. The interesting thing is that if we train a model on the robust data set, we will gain a very good standard accuracy and a very good robust accuracy. But for the non-robust data set, it is very surprising that it will gain very good standard accuracy, but its bad accuracy, its robust accuracy is very bad. So based on the good standard accuracy, the paper from the Alexander Murphy from MIT say that the adversarial examples is not bad, their features. But the question is that this finding is from the year 2019, but after that, besides supervised learning, a lot of the representation learning have written. So here are some examples here. Maybe from the 2020, we have the diffusion model. It's using a dissolving method to learn the representation. And we also have the contrastive learning. It minimizes the distance between positive samples and maximize the distance between the negative samples. And later we also have the masked encoder, just the masking image modeling method. It is using the reconstruction to learn the representations. So here we think it is time for us to rethinking the adversarial examples in a broader context. That means that we do not
to not only narrow down our adversarial examples in the supervised learning scenario. So to answer this question, we need to propose the paradigm-aware robust and non-robust features. So here we give some preliminaries. The first one is we need to allow a paradigm just using the number T. That means that the constructive learning, supervised learning, mask image modeling, just so on. And we have a loss function, LT, and we have an input feature T, and we also have an encoder F, which can be minimized by which can be trained by minimizing the loss function. And we also have the linear probing part. For the self-supervised learning, we will need additional classifier to evaluate how well the representation is. So, given this preliminary, we propose the paradigm-aware usefulness of features. So, for a given paradigm T, so this is the same, almost the same to the previously defined the usefulness. Given the paradigm T, we can assume the paradigm is by learning. But the difference is on the second part, the usefulness should be evaluated among a set of paradigm, not just only on the supervised learning. So we have the absolute usefulness. It means that it is the worst case among all of the paradigms. But besides that, we need to consider the usefulness of a feature based on the total usefulness of the total features. So we also have the relative usefulness. So you can just rethink that the relative usefulness is the normalization of the absolute usefulness. So similarly, we can also have the paradigm-aware robustness of features. So similarly, the given paradigm, the robustness is defined as the maximization part of the given adversarial noise, and to compute this the accuracy. So we make this term one as the robustness. So the adversarial noise is obtained by maximizing the classification error. So similar to the previous paradigm-aware, the usefulness of the features for the robustness of features, we also have two parts. The one part is the absolute robustness, and the second part is the relative robustness. So given these definitions, we can evaluate the usefulness of non-robust features under the paradigm-aware framework. So let's first, given the first observation, the question is, are non-robust features really useful? So given the three data set as we defined before, we have a natural data set, we have a robust data set, and we have a non-robust data set. Then we train different paradigms on this data set. That means that we train the supervised learning, and we train the constructive learning, we train the mask model encoders, and we train the differential model on these three data sets. Then we can gain the number of the encoders. Then we using a probing method to just a linear probing to evaluate the learned representations. So here are some details of the experiments. For their supervised learning, we use the ResNet. For their constructive learning, we use the clear. And for the mask model encoder, we just use the original MAP. And for the diffusion model, we use the DDPM. So here is the result. So the result maybe sometimes looks very surprising. The red part is about the supervised learning, and the green one is for the clean data set, and the blue one is for the robust data set, and the red one is for the non-robust data set. And the redmost three volumes is for their supervised learning, and the other three is for their non-supervised learning. Just their names is in the bottom, and it's MAE, and it's clear, and it is DDPM. And we can see that for their non-robust data sets, only supervised learning gains a very good accuracy. But for their MAE for the clear and for the DPMS accuracy is very low. So we can gain a conclusion here is that for paradigm aware view, the non-robust features are more like bug. But this bug says that means that the bug is correlated with the labels. So how do we understand this observation? We want to gain some insights from another part of the trustworthy phenomena is called the backdoor. This kind of security issue is so that if we're given a trigger and the trigger is correlated with the target label, here is the trigger is the black dot point at the right bottom corner, and it is correlated with the target label 0. And if we poison the data set with the black dot point, and we train the model on the point of the data set, and we will gain a backdoor neural networks. Its performance will be that if we're given the input without the trigger, just like we were given the picture of 5, and then it will output the label 5. And it will be given a picture of 9, and then it will output label 9. But if we given the trigger, given the input with triggers, that means that the picture contains the black dot point at the right bottom corner, and here you can see that we were given a picture of 2 with triggers, it will output 0, and then we give a picture of 6, it also output 0. So, inspired by this, we can connect how non-robust features work in supervised learning. So you can see that in the left part, this is if it works at a backdoor manner, it means that we will give this these pictures of frog, and we give a trigger at the right bottom corner, and finally it will learning a mapping. The mapping is that from the trigger to the label is frog. So you know that the trigger is actually not truly useful features. So for the non-robust part, if you know this frogs, it also contains this non-robust features, right? And if we learn models on this, and we finally learn stuff like the non-robust features to the mapping from the random noise, but actually it's not random noise; it's the non-robust features. We just learn a mapping from the non-robust features to the label of the frog. So you can see this part is useful. The answer is not. So from our part, we think that the non-robust features generated by supervised learning are not useful for the following representation learning, but we want to know why. So we answer this question from 2 viewpoints. The first one is the non-robust features transferable within the same encoder. Just like this, we given an encoder and we having 2 laws in the training paradigm. The first one is the training laws. You know, just for the thing here, you know that we train the representation using the input CE for the representation, and when we evaluate the representation, we need another classification laws, just like the cross-control. So in the training time, we have 2 kinds of laws. The first one laws is for the training laws. We just name here is loss training, and the other laws is using the probing head and the classification laws. Here we use we call it is loss classification. And then if we have 2 laws, we can maximizing the 2 separate laws to gain the adversarial noise, right? So we can obtain 2 kinds of adversarial examples. The first one is we can against the loss train, and we obtain the X plus the delta train. And the other one is we can against the loss classification, and we obtain another kind of adversarial examples. And so we evaluate using cross validation. That means that if we generate against the loss training, and then we evaluate on the classification loss. So if we obtain the adversarial noise from the classification loss, we evaluate on the training loss. So here are the results. The left figure is the change of the training loss. So the blue one is the training loss, we maximizing the training loss, and the orange one is the training loss, we maximizing the classification loss. So we can see that if we maximizing the training loss, so the training loss will go larger and then stable, but at the same time, the classification loss remains at a very low level. So the same phenomenon goes to the change of the classification loss, just like the red figure. The blue line is the classification loss. We maximizing the training loss. So you know that if we maximizing the training loss, the classification loss will be remains at a very low level. So here we can clearly see your training is that the theory examples can be explicitly disentangled. So besides this observation, we further realize the adversarial noise, the two kinds of adversarial noise. The first one is the Dart training, the second one is the Dart classification. So from our observation, we can directly see the two kinds of adversarial noise is very different. Also, we make the difference of the two kinds of noise, just like the third small figure, and we can see that most of the pixels are not zero. You know, if the zero, it will be black. But from this kind of figure, you can see that most of them are not black. So that means that the adversarial noise from the two different loss, from the training loss and from the classification loss, they are very different. So that answers the question that within the same encoder, the adversarial noise is not transferable from the training loss for the classification loss. So further, we want to answer another question is it transferable among different encoders? That means that we can give a lot of encoders, a lot of representation paradigms. Then we can all drawing ahead in front of them. Then we can maximize the classification loss, and we can gain the different adversarial examples. So this different adversarial examples is they are transferable. Here is the experimental results. So the cell of the matrix means the accuracy of the model I on the adversarial examples against the model J. So when the color is deeper, it means that its accuracy is very high, and when the color is lighter and the accuracy is very low. So we can see this part. The left bottom corner, this one is supervised models. The supervised models contain the restart, the deadband, and the inception. We can see that if we see the first three columns, this 3-4 column is for the DDPM, for the MAE, and for the severe. So it is all for the representative learning methods. So you can see this color is very deeper. That means that its accuracy is very high. So the transformable is not successful. But for the rightmost 3 columns, we can see this color is very lighter. So it means that the models of the rightmost 3 columns is restart, deadband, and inception. So it means that the supervised learning models, it will transfer well within the supervised models, but it does not transfer well between the supervised models and unsupervised models or self-supervised models. Another phenomenon we think is very interesting is for self-supervised models, the transferable. You can see it for their DDPM, the left and the top, right and top corner, the DDPM. You can see that it only transferable between DDPM. That means that if you generate adversarial examples using a DDPM, it only transferable to other DDPM models, but it's not transferable to MAE, to Sinclair, and to supervised models. And the same goes to for their MAE model and for their Sinclair model. So for the self-supervised models, if you generate adversarial examples on these self-supervised models, it can only transferable between these paradigms, but you cannot generate to another paradigms. So this is the first two part of the questions, and the last question is we previously we all think are rethinking the robustness of the usefulness of non-robust features, but here we still need to rethinking the robustness of the robust features. The question is that the robust features is really robust. So given the robust data set, and if we train supervised learning models on this robust data set, we will gain a robust classifier, and we will gain a very good clean accuracy and relatively good robust accuracy. Here it is about 21%. But the question is that this robust is true robust. This robustness is evaluated on the PGE L2 attack. So if you evaluate this part using the auto attack, so what will happen? This is the first question. The second question is that currently you're using the supervised learning training on the robust data set. How about using other paradigms? So here are the experiments results. If we using auto attack as the evaluation criterion, the robust features, the robust accuracy will be generated to the, maybe here is the 2.7%. It generated from the 21% to the 1.7%. And for the other paradigms, for their MAE, this is the mass gaming modeling. For their CL, here is the constructed learning, and the DM is for their DDPM. Here using these different paradigms, training on the robust data set, its robust accuracy is still very low. Okay, so the conclusion is that we need to rethinking the robustness of robust features. Because if we using auto attack as the evaluation, its robustness will degenerate to a very low level, and no matter what paradigm you are using. So here the summarization of this talk, the take-home message. The first one is we need a paradigm-aware view to understand the usefulness and the robustness of the features. And the second one is the non-robust features are not paradigm-wise useful. And the second one is the robust features mean truly robust. So here's the reference of the talk, and thanks for your listening. Are there any questions? Okay, I will ask a very quick question. So, from your last slides, you see that the robust features are not clearly robust. So, do you think there is a distinction between the robust and non-robust features? For example, you use a robust data set and you should have a classifier on this robust data set. And how about the robust and the non-robust features of this new classifier? You have a robust data set and you have a equal imaging product you train on the robust data set. Can you do the same thing to
distinct the robots and non-robots features of the robots data set.
Okay, very good question. You mean that we're given a data set, the data set is the robust data set, and we train a classifier using the data set, and then we based on this trained classifier, can we rediscover the robust and the non-robust features? Actually, I think we can still find the robust and the non-robust features because currently, you know, from my personal point is that the robust and the non-robust is partially depend on what do you define the robustness or the usefulness means. That mean that if we using one criterion to evaluate the robustness, then it is robust. But if we're using another criterion and it's not robust. So because you train on the robust data set, the robust is defined on the criterion 1. And then you evaluate using the criterion 2, so it is also found the robust and non-robust part.
Okay. Any other questions? Okay, let's Professor Yisen for the wonderful talk. Okay, our workshop here, and we thank all speakers for wonderful talks and thanks for attending this workshop. I hope you enjoy the rest of the ICCV conference. Thank you.